So we're gonna like make your slides and share, and then like we would put like a video, and then I'll do an intro as he said, and then like you can share back.
Okay.
If that's okay.
Sounds good. Yep. Are you guys hearing any construction noise?
No.
That's awesome. Okay, yeah, they're really going at the building next to mine. So
we're gonna like
apologies in advance.
Make your slides and share, and then
yeah.
Sorry, it was just my YouTube on the parallel stream that was repeating. Excuse me, I wasn't like repeating myself 25
That's all
times.
Right. Even if you need to repeat yourself, go for it. But yeah, no, I figured it out after I clicked the button.
Okay, I think we're ready.
I'm at meeting.
Yeah.
Hello, everyone. I hope you can hear me well. I'm just going to keep admitting people. All right. So if you can hear me, like indicate, but I think like everyone can hear me. Okay. Good morning or good afternoon or good evening, depending where you're located. Welcome to our second data science summer school organized by Hardy School Data Science Lab and generously supported by Hardy School this year. So we're super grateful for that. Just want to note a couple of organizational and technical details about the summer school in general for this year and this particular workshop. So first of all, I want to say that this year's summer school, as you might have noticed, began with some introductory classes for programming and mathematical foundations for the success of the data science. This part of the technical preparation is kind of a part of pre-fresher for Master of Data Science for Public Policy program that we have here in Hardy. But as you might have noticed, it is obviously open for everyone interested. So we are really happy to see you all here today and welcome. And I just want to note a couple of details about our Zoom and YouTube stream. So if you are on Zoom, welcome. And you might have noticed that you're muted upon entry and probably your cameras are off. Please do not unmute yourself during the lecture. You can keep your video on if you want, but you can also put it off. It's kind of up to you guys. We would kindly ask you to put your questions in the chat if you do have a question. But if you want to speak up and ask your question out loud, please raise a hand. And whenever is a good time, we will let you guys ask your question. If you are joining us on YouTube in the parallel stream session, I actually want to say that we do still have spots in Zoom, so you can jump in on the Zoom call. If you do prefer to stay on YouTube, it's great. It's up to you guys. But please put your comments or questions in the live comment box on the YouTube. We will try to answer your questions right away there, or if it's something more complicated, we will address it to the instructor just like by asking it out loud. And finally, I just want to note that the Zoom session is being recorded. So you should be aware that if you do speak up or like you turn your camera on, you are agreeing to automatically being recorded. And thanks so much for following these rules. And I want to welcome you to our 5th workshop in this series of events. And today we have Probability and Statistics for Data Science. And let me introduce you Dr. Henry Pascal, who is going to be our instructor today. Henry is an assistant professor at the IE University in Madrid. He studies international relations using game theory and statistics. And in particular, his research focuses on transnational terrorism, foreign aid, international organizations, and interstate conflict. Henry, without further ado, the floor is yours. You can share your screen now, and everyone, good luck and have fun.
Great. Thank you, Olga, for that introduction. Let me get my slides up here. Okay, so should be able to see my slides now. As Olga said, I have a pre-course, mainly focusing on probability, although we will talk some about statistics today. And, just to reiterate, really fundamental for data science, and perhaps those connections are obvious, but we can make some as we go along today. One thing I'll say here is, I've heard the organizers told me that, you guys are a really heterogeneous group with a lot of different backgrounds and levels of familiarity with probability. So for that reason, I've started out things fairly basic, and then we kind of build up from there. All that to say that if you're like very strong in probability, this might not be that interesting to you. Who this is really geared toward is folks who need some backfill or a refresher in probability, right? So if you've slept since your last probability class, this may be helpful to you. Okay. And just to reiterate, like Olga said, if you have any questions, please just put them in the chat, and I'll be happy to try to answer those for you. Okay, so what I want to cover today, first, I want to talk a little bit about set notation and sample spaces. Okay, these are going to be kind of the first primitives, if you want, of building up a theory of probability. Once we have those sample spaces defined and are comfortable sort of dealing with set notation and some basic set operations, we'll start talking about probability and random variables. Okay, and these will really, kind of be the workhorse of lots of different, data science techniques and algorithms. What we'll focus on today, though, is really getting kind of good fundamentals and dealing with probability, characterizing the probability distribution of random variables. So, the likelihood, you can think of probability distribution as describing the likelihood of a random variable taking different values. Okay. And really getting comfortable with that, for instance, things like joint distributions of two variables, which will lead into a discussion of conditional probability. Okay. And we'll talk a little bit about Bayes' rule there, which in one sense, it's a way of flipping around a conditional probability. In another sense, it's a learning algorithm. But we'll talk through some examples there. Then we'll talk about expected value and variance. So once you have characterized the probability distribution of a random variable, often you'll be interested in things like its mean and its variability. So we'll talk about that. And finally, I want to talk a little bit about descriptive statistics at the end, and there we'll introduce the idea of a sampling distribution. Okay, so for instance, for a statistic like the sample mean, especially if you're using the sample mean as like an estimator of population mean, you might be interested in how your sample mean is going to behave under repeated sampling. Okay. So we'll end on that note. That's sort of where we're headed for today. Just quickly, I did put together a syllabus for you guys. See if I can grab it here, just to give you. Oh, it's not moving for me here. I did put together a syllabus for you guys. I believe it's posted on the course page. Basically grabbed from 4 different books. The 2 Roundtree books are fairly basic and not too rigorous. The Agresti book, thanks, Huey. The Agresti book, a little more rigorous, but more kind of geared toward, social sciences. It's the book I usually use in like a undergraduate intro to statistics course. And then we have the Amai, Wooldridge, and Wasserman books, which are all good in different ways and a bit more rigorous. And then finally have the Casella and Berger book, which is a really, really quite rigorous and sort of concrete presentation of a lot of these ideas. Okay, so depending on kind of where you're at, those are the books I'd recommend, taking a look at some of those examples. Some of the examples I'll present today draw pretty heavily on Casella and Berger and also the Wasserman text. Okay, so just to reiterate, what the video was saying and Olga was saying at the beginning, like, why do we want to learn about probability theory anyway? Well, for those of you starting the master's in data science, maybe this is fairly obvious. Like data is often best modeled by either uncertain or stochastic processes, and that's going to necessitate being able to reason about uncertainty. Probability is a really good tool, not the only tool, but a really good tool for doing that. And you can think here of probability as a mathematical measure of uncertainty, or put another way, a measure of likelihood of different events. Okay, so let's define some things, like for instance, event, let's talk about the likelihood of an event. Let's define some of these concepts. And to do that, I want to draw upon set theory. Okay. Set theory is just a way of reasoning about different groups. Okay, so for instance, consider a set A consisting of the following elements. We have 1, 5, 3, 6. Okay. Each one of those is an element of A. Okay. Each of those numbers forms an element of the set A, and we write A and A. So this symbol between the lowercase a and uppercase a just says that lowercase a is an element of the set A. Okay, so 1 is in A, 5 is in A, 3 is in A, 6 is in the set A. Okay, so one thing to note here is, while a lot of the examples I'll give are quantitative, the elements of a set need not be numbers. Okay. So for instance, consider the following set of words. I'm going to denote by omega. In the following quote from Democritus, okay. And I'm not a political theorist. Maybe the translation isn't the best here, but the quote basically says something like, "Everything existing in the universe is the fruit of chance." It's a supposition about probability, right? So that's a set. Each word is an element, right? And I've just separated each element with a comma. One thing to note when you're dealing with sets is order is not important. So the following on the last line there is equivalent to omega. And so just rearranging the words here, say the chance of fruit existing in the universe is everything. And set notation, those are equivalent sets. Okay, the order is not important here. One other idea here is the cardinality of a set. By that, you can think just the size of the set. Just refers to the number of elements, right? The number of elements in the set. So for instance, what's the cardinality of omega? Somebody just put it in the chat. What's the cardinality of omega? Yeah, 10. There's 10 words there. There's 10 elements. Very good. How about A, that first one with the numbers? It's the cardinal. Yeah, 4. Great. It's just the number of elements in the set. Okay. Okay, so we can talk about the relationship between two sets and have a lot of different operations to do that. The first I want to talk about is the intersection. So for instance, the intersection of A and B is given here, right? It's just that sliver that's both A and B, right? So this this sort of upside down U denotes the intersection. Okay. One way you can read it is like A and B, or the intersection of A and B. That's the intersection. Let's just do a really basic. Sorry, just a sec. If we have A is, sorry about my handwriting. And when I was very young, when I was like 6 years old, my teacher would count things correct if she couldn't tell what I wrote, and it ruined me. So let me know if you can't tell what I'm writing, but set A is going to be 0, 1, and 2. Okay, and set B, let's have B 1, 2, 3. Okay. So if A is 0, 1, 2, and B is 1, 2, 3, what's the intersection of A and B? Yeah, 1 and 2. And that's because the elements 1 and 2 are in both A and B. I saw one question. Someone was just checking that they're understanding here. So like 1, 2, 3, 4, if that was A, and set B was 3, 4, 5, 6, then correct. The intersection would be 3 and 4, right? 3 and 4. Okay, so that's the intersection. The union you can think of as A or B, right? So if A, again, I'm just going to put it in the chat. Maybe it's a little easier. 0, 1, 2, and B is 2, 3, 4. What's the union of those two sets? I just put them both in the chat. Maybe that'll be a little quicker than me scribbling. Yeah, the union is just 0, 1, 2, 3, 4, right? It's all elements that are contained in either set, including their intersection. Very good. Okay. Okay, so that's intersection and union. Yeah, very good, guys. You guys are getting it. Okay, and again, these are like probably familiar operations to a lot of you guys. The other one I wanted to mention was complement. Okay, so the complement of B is just simply not B. You can think of it as not B, right? So that blue area on the left is the complement of B for, you can think of that as like the universe on the left, I guess. For the universe on the right, the complement of B is that shaded area, in A and also Z, right? So if A is 0, 1, 2, and B is 2, 3, 4, what's the complement of B? So just the same sets I just used. What would the complement of B be? So 0's in it, right? 0, because it's an A, but not in B. But there's one other element we're missing there. Yeah, it's 0 and 1. 0 and 1. Very good. Okay, you guys tracking with this stuff so far? Any questions about kind of these first parts of set notation? What we'll talk about next is some of the properties. Okay, fantastic. Yeah, we can think about like the complement of the intersection, right? So again, you denote the complement with a C, or you'll also see it with like an overline bar, like I've written on the slide here. And so we can see the complement of the intersection of A and B is that shaded area in A and that shaded area in B, right? Another way of thinking about, something really similar to complements is the set difference. Although I did include an example here on the right that hopefully shows the difference between just thinking about complement and set difference, right? So the difference between A and B, the set difference A and B, is just that shaded area of A for the example on the left. For the example on the right, the set difference of D minus E is the shaded area in D, right? And we can see the difference here is when we're just taking the complement of B, it wasn't specific to A, so we have the shaded area in Z left. But now we don't shade that area in Z. It's just the area in D that's not also in E. Okay, so a little bit of a subtle difference between complements and set differences there. Okay, so that's some basic operations you can do with sets. Next thing we need to define is the empty set. Okay, this is just a unique set with no elements. Okay, set with no elements. And you see it denoted as the 0 with a slash. Well, I guess it's mirrored, so slash through it. Okay, so for an example of an empty set, or example of the empty set, if you like, since it is unique, you could consider the intersection of the set of even numbers and the set of odd numbers, right? That's going to be the empty set because no numbers are both odd and even. You could also think about the set of prime numbers greater than 2, right? So all prime numbers except for 2 are odd. So the set of prime numbers greater than 2 is going to be the empty set. There's no numbers like that. Okay, so that's the empty set. Okay, we can also think about subsets. So a subset for two sets, A and B, if every element of A is also an element of B, then A is a subset of B. Okay, A is a subset of B. The line, you won't always see people use the line. The line's used to indicate, you can think of it as equality or not. So not all textbooks are super strict about this. You may just see it without the line, but they're still sort of allowing sets that are equal to be called subsets. You know, that's fine. It's just something to note. If you do see the line, they're indicating that it could be equal. What I mean there is, like, for instance, is B a subset of B? Well, if we allow equality of sets, then yes. If not, then we'd say it's like not a proper subset of B. We won't do too much with that today, but I just want to bring it up kind of in terms of notation. Okay. We will use the idea of subsets today, but we won't make a big deal about this distinction between equality and not. Okay, so that's subsets. One thing that'll be useful, especially anytime you're thinking about like a coordinate system, but even more generally, you think about like the Cartesian product of two sets. And the Cartesian product of two sets, column A and B, is defined as the set of all ordered pairs, A comma B. And you can think about, generalizing this to triples or intuples, you can generalize it. But each element of that so the Cartesian product itself is going to be a set, and each element of that set is going to be an ordered pair, A comma B. So for instance, if A is the set of outcomes from a coin flip, and B is the outcomes of a six-sided die roll, what's our Cartesian product? Well, it's going to be an ordered pair. The first part of that ordered pair is heads or tails. And the second part of that ordered pair is going to be the outcome of the six-sided die roll, right? So think about that. Let's maybe that's actually reasonable to write in the chat. Just write a few elements of that Cartesian product. We don't need to be fully, yeah, okay. So Sada Yapan's got it here, right? So heads, comma 1 would denote getting heads on the coin flip and rolling a 1 with the die. Perfect. And as they've indicated, that goes all the way through tails, comma 6. Okay. Okay, so that's what the elements of that Cartesian product look like. Putting a couple things together, like what's the cardinality of that Cartesian product? Put another way, how many elements are there? Yeah, there's 12, right? Heads 1, heads 2, heads 3, heads 4, heads 5, 6, that's 6, and then same for tails. That gives you 12 elements. And that's quite right. As Timur indicates, we can just take the number of elements, put another way, the cardinality of the first set times cardinality of the second set. Very good. Okay, so a few properties of sets, some kind of basic properties of sets. So we have commutativity. Okay, so the intersection of A and B is the same as the union of A and B is equal to the union of B and A. And got a little tongue-tied, but the same goes for the intersection. So I don't have them written for the intersection here, but the properties are both in the Wasserman book and Casella-Berger book. Same deal though. It's the intersection of A and B, same as intersection of B and A. So, the commutative property holds here in a nice way. Also, associativity holds. So the union of A and, the union of A with the union of B and C is the same as the union of A and B with C, right? So things, the associative property holds in sort of an intuitive way here. We can also distribute, okay? Sort of similar to multiplication, we can distribute. So the intersection of S with the union of T and U is equivalent to the intersection of S and T with the intersection of S and U, right? So I've just distributed out that intersection between S and over the union of T and U, if you like. Okay, so distributive law holds here. And then just a couple other little facts here, like the complement of the complement of S is just equal to S, right? Okay, so that's what I wanted to cover on kind of set notation, a little bit of operations on sets. We'll use that kind of throughout the discussion today to kind of build up ideas. The first idea that we'll use it for is to think about sample spaces. Okay, and a sample space, we're going to note it by omega, is the set of possible outcomes of an experiment or a process. We're going to call each outcome, each element of that set, omega, like lowercase omega here. And we can think of subsets of omega as events. And we'll denote those by A. Okay. And it's on those events which will eventually assign probability. Okay, so think about, we have the sample space. We'll see some examples here in a minute. We have the sample space. We're going to find events as a function of the elements of that space, and then we're going to assign probability to those events. Okay, so for instance, if we flip one coin, what's the sample space? Pretty simple sample space here. Put another way, what are the possible outcomes? Yeah, heads and tails. Very good, heads and tails. What about daytime high temperature? Yeah, it's just yeah, I mean, depending on the scale, it's going to be real numbers or positive real numbers, I guess, if you're using Kelvin or something. But yeah, in general, could be just any real number, right? From negative infinity. I know there's like a theoretical bound on how low temperature can go. So it just goes from that to basically positive infinity. Basically, my understanding is physics isn't well enough that I know if there's like a maximum temperature, but I know there is a minimum one. But that's good, right? So it could be any number there. So here we have a sample space that's infinite and not countable, right? So that's notable. How about reaction time? Yeah, thanks for the minimum there. Yeah, I always get mixed up on these different scales. But that's right. So it goes from whatever that minimum is to, whatever the maximum is. Probably positive infinity, but I'm honestly not sure. How about reaction time? So you can think of this as like, a lot of times in experiments, like if someone's having like neurological issues and they want to test their reaction time, they'll show them a prompt and have them push a button, right after they see the prompt. They say, just do it as quick as you can after you see it. And that's right. So it's we think of it as in seconds, goes from 0 to positive infinity, right? So the person just sits there and never presses the button, I suppose. Yeah, so we'd have to think some like whether we'd want to include positive infinity in the sample space or not. Again, if you have someone who never presses the button, maybe you'd want to include it. But Hayu's suggestion of not including it makes sense if we assume that like they always press the button eventually. Okay. So let's start thinking about events then. You guys have a good handle on this idea of sample spaces, possible outcomes. Let's start thinking about events. And we could think about events, again, as a function from the outcomes of the sample space, omega. So for instance, flip one coin, you can get heads or tails. An event would be you get more than zero heads, right? That's defining an event. There's only one element of the sample space in that particular event. It's when you get heads on that flip. What's a possible? Let's try to define an event for daytime high temperature. What's a possible event there? Well, a really notable one here in Spain has been like, is the daytime temperature greater than 40 degrees, right? And we could also think about, equal to 40 degrees. That'd be another event. Less than 40 degrees be another event, right? How about reaction time? Okay. Well, reaction time similar, so I won't belabor it here, but one event could be like, well, it took them less than 5 seconds, right? Less than 5 seconds. Okay. And there'd be a lot of, and really an infinite number of outcomes that fit that event, that are in that event, if you like, right? So if it takes them 1 second, if it takes them 2 seconds, 3 seconds, 1.5 seconds, 1.672, 134 seconds, so on and so forth, right? So again, you can think of events as just a function of the outcomes. Okay, we're going to call 2 events, call them A1 and A2, disjoint, okay, which you can read as mutually exclusive, if their intersection is the empty set. This just means they never occur at the same time, basically, right? We can generalize this to more than 2 events with this idea of pairwise disjoint. So call 3 events, A1, A2, and A3, pairwise disjoint if the intersection between each of the events is the empty set for all events that aren't equal, right? Okay, so this is the idea of like mutually exclusive events. So for instance, 2 mutually exclusive events for reaction time is it takes you less than 5 seconds to respond. And so that'd be like A1, A2 would be greater than or equal to 5 seconds, right? Those are disjoint. They're mutually exclusive. Their intersection is the empty set. Okay, so thinking about assigning probabilities to events, we can use the Discrete Uniform Law. And this says that assume that our sample space omega consists of n equally likely events. Okay. And assume that event A consists of k elements. Well, then the probability of event A is just going to be the cardinality of A divided by the cardinality of omega. Okay. So for an example here, suppose we roll a 20-sided die. Okay. Use this fact. Okay. Use this fact about the probability arising from the relative size of event A versus the sample space. Let's use that fact to derive some probabilities of different events that could happen when we roll a 20-sided die. Just as a quick sanity check, like what's the sample space look like if we roll a 20-sided die? Don't have to write the whole thing. Yeah, it's just 1 through 20. Great. So what's the probability of the following events? So say the event's rolling a 1. Yeah, 1 in 20, right? Because there's only one outcome that gives you a 1 as your event, and there's 20 elements. Great. What about rolling an even number? It's going to be 1/2, right? Because half of the elements of the sample space are even, and the other half are odd. How about rolling a prime number? Okay, so this one takes a little bit longer because we have to remember like what's the prime numbers between 1 and 20. Hopefully I have them all here. So I have 2, 3, 5, 7, 11, 13, 17. Am I missing any prime numbers there? I don't think so. 1, 2, 3, 4, 5, 6, 7. I see people getting 8. Which one am I missing? Oh yeah, 1. Duh. Okay. So, oh yeah, you're right. You're right. Okay, so I count 7. I count 7 primes, right? So I give us 7 over 20. Yeah, that's the list of primes I got too. Lena and Silavo. Thanks for that. Oh shoot, 19. Duh. Okay. Sorry for saying duh. I shouldn't say that. Oh yeah, 19's prime. Okay, so that gives us 8. So it's 8 over 20. Like a lot of you guys indicated, right? Okay. How about rolling a number greater than 20? Yeah, 0, right? There are no elements greater than 20 divided by 20. That's going to give you 0. Okay, and to illustrate something a little bit like, and those of you who know the rule already, probably pretty quick to figure this out, but what's the complement of each of these? So what's the complement, the probability of the complement, rather, of rolling a 1? Well, it's just going to be 19 over 20. Yeah, it's just 1 minus the probability, as Bildora suggested here, and we can do that for each of these. So rolling an even number, we figured out earlier that the probability is 1/2. That means the complement is 1/2, right? It's just 1 minus what we got before. Rolling a prime number, we got 2/5, right? Because there's 8 elements that are prime out of 20 elements in the sample space. And so, yeah, it's going to be 12 20ths, 3/5. Rolling a number greater than 20. Well, the probability of that was 0. So the probability of the complement's 1, right? Very good. Okay, so just a little bit of practice here, simple example, but basically using this discrete uniform law to figure out probabilities based on the relative size of the event versus the sample space. Yeah, I don't know D&D. I know other games, and I have a lot of dice, but all right, let's see. So that's what I want to talk about for sample spaces. Now let's use that to really start thinking about random variables. Start thinking about random variables. Okay, so Probability is just a means of quantifying uncertainty. Sarah's putting you on the spot. Okay, so we can think about uncertainty as arising from lots of places, right? So we're kind of in this world of uncertainty. Then we think about it as just like inherent variability in the process we're interested in. Could also think about it arising from the fact that we often, or I would claim probably always, have an imperfect model. Certainly for, they talk about data science for public policy. Certainly if we're talking about public policy or social sciences, we're in this world where we don't have, sorry to put you on the spot for it, although it was really Sarah. We might have an imperfect model, right? And so we might get uncertainty due to that. Could also have some incompleteness in our observation. We might not be able to observe everything, and that would cause uncertainty. The idea of probability here is for each event, just like we just did using the Discrete Uniform Law, for each event, we want to associate a function P of A, P of that event. For each event A, associate a function P of A. That satisfies the following axioms. Okay, so these are the Kolmogorov axioms. I know I'm pronouncing that wrong. And they're as follows. So the probability of A is non-negative for all events in our sample space. Okay, so probability can't be negative. The probability of the total sample space is 1. You can think of this as, something has to happen, right? Something has to happen. And if events are so someone's pointing out like, oh, this is like classical probability. In fact, these axioms hold regardless of your interpretation of probability. And we'll talk a little bit about the frequency interpretation and the Bayesian interpretation of probability. Not too much about classical probability today, but regardless of your interpretation, these axioms hold, right? So these are just kind of general requirements we're putting on a probability function, right? So when we think of probability as a function on events, how we interpret that function is a separate question, right? And we'll talk a little bit about that here in a bit. But yeah, certainly these axioms apply if you have like a classical interpretation of probability, but they also apply, for other interpretations. Okay, so it has to be non-negative. The probability of the sample space is 1. And if we have a set of events, A1 through AN, let's call AK, and they're pairwise disjoint, okay, so again, think mutually exclusive, then the union of those events, the probability of the union of those events is just the sum of our probabilities, right? So this is like the additive rule of probability. If they're disjoint, we want to know the probability of the union. Then we just sum up, the probabilities. If they're not disjoint, there's some complication here because we have to make sure not double count the intersections, right? So we have a really similar rule, really similar axiom, which actually just follows from these 3 axioms, which is why I don't have it listed here, but we have a really similar result that for events that aren't pairwise disjoint, the probability of the union is just the sum of the probabilities minus the intersections here. And we'll talk about that here in a moment. Okay. We'll talk about it right now. Sorry, here it is. So what I was saying, here it is written, is that the probability of the union of A and B is more generally, so these 2 events aren't necessarily disjoint, is the probability of A plus the probability of B minus the probability of A and B. okay, the intersection. And that's what I mean. We need to subtract off that intersection. Otherwise, we'll end up double counting it. Since the intersection by definition is in both A and B. If A and B are disjoint, what's the last term of this equation here? What's the probability of A and B if A and B are disjoint? Yeah, it's 0, right? So this property is fairly easy to show. I'm not going to show it here, but it's fairly easy to show that it just follows from these axioms, right? And there's a nice presentation of that in Casella-Berger if you're interested. Another property we can derive is that the probability of the empty set is equal to 0. Okay, this basically follows from the second axiom pretty quickly. And then the last property I want to, I think the second to last property I want to highlight is that if A is a subset of B, then the probability of A is less than or equal to the probability of B, right? So again, you can think about that discrete uniform rule as an illustration of this. If A is a subset of B, then it is less to than or equal to in cardinality B, right? A is no bigger than B. And so that means that since they're in the same sample space, the probability of A can be no bigger than the probability of B. Again, if A is a subset of B. And then as a lot of you guys noted when I was asking about the probability of complements, again, you can figure this out from the discrete uniform law that covered. It also follows from the axioms here that the probability of the complement of A is just 1 minus the probability of A, right? 1 minus the probability of A. And this again basically follows from the first two axioms here, that it's non-negative and that the probability of the sample space is equal to 1. Okay. And this last fact's fairly useful, especially in sort of mathematical statistics. Sometimes it's really hard to figure out the probability of A, but you can figure out the complementary probability more easily, and so that can help you out. Okay, so that's the axioms of probability. Okay, that's just requirements we're putting on any probability function. Okay. Now, a random variable is a function from the sample space onto the real numbers. Okay. For example, if we toss 2 dice, the random variable, we could define a random variable as the sum of the 2 numbers. Right? We could talk about the probability of each of those different sums, and we could use the discrete uniform rule to do that. Another example is toss a coin 10 times. Random variable is the number of heads, right? Another one would be the reaction time to press a button when prompted, in just the number of seconds. Okay. Just to show that from the same sample space, we can get different random variables. For this first one, tossing 2 dice and defining the random variable as the sum of the 2 numbers. What are some other possible random variables we could define from tossing 2 dice? So that would be the sum, I think. Okay, sorry. I think some confusion because I showed like a lot of different things. Just for tossing 2 dice, right? We defined a random variable as the sum, but we could define a lot of other random variables, right? So Xiaoyu says the product, right? So great, that's exactly right. The ratio, right? The ratio of the number on the first die to the ratio on the second die. The difference, right? These are all just different random variables that we're defining on that same sample space. Great. And you know, I also want to point out the random variable need not use all the think about it as like information in the sample space, right? So we could call the random variable the number on the first die, right? And just ignore that second dice. That'd be another random variable, arguably same sample space. We're just ignoring the second die. Okay, so let's get into interpretation. Somebody brought up classical probability. I want to focus on kind of two main interpretations of probability. A subjective or Bayesian interpretation of probability. So think about probability as a degree of belief. And then the frequency interpretation of probability. Here we're going to think about probability as a long-run relative frequency. Again, these are going to have the same axioms and mathematically, you know, operate in the same way. Really, it's just a matter of interpretation. Okay, so under the subjective interpretation, also known as Bayesian interpretation of probability, we can think of probability as a degree of belief, or degree of belief that some particular outcome will occur. Under this interpretation, you can think about, you know, if you're risk neutral, okay, you can think about the probability of X as being the most you would pay for a bet that'll pay off €1 if X occurs and pays nothing if it doesn't, right? So if you're willing to pay 50 cents for a bet that will pay you $1 if the event occurs, nothing if it doesn't, well, then you must be willing, then your belief about the probability of event X occurring must be 0.5, 50%, right? Again, it's just assuming risk neutral here for easy math. Yeah. So kind of hopefully silly examples, like if you'd pay 50 cents for a bet that pays €1 if former President Trump gets elected in 2024, then you must think the probability of that happening is at least 50%, right? If you're willing to pay 50 cents for that bet that's going to pay you €1, if he gets elected, then you must think it's at least 50% likely. You know? Otherwise, you wouldn't take the bet. So you can think about it as like a degree of belief. So that's one interpretation, and a really common interpretation, especially in a lot of machine learning, really common interpretation. The other interpretation I wanted to kind of signpost for today is the frequency interpretation. Another really, really common interpretation of probability, and it's where probability is the relative frequency of occurrence of some particular outcome if the process were repeated a large number of times, where the number of times approaches infinity. So, for example, if you flip a fair coin over and over again, in the long run, you would get half heads and half tails in the long run. So you say the long run relative frequency of heads is 0.5. And that means that the probability of a coin coming up heads is 0.5, right? Sorry to repeat myself there. I do want to pull up a little applet here that I think illustrates this decently well. Let me just, there we go. Pull it over here. Okay. Hopefully you guys see my screen okay. This is an applet from the Rossman collection of applets, some nice ones here. And this one just want to use to think about this idea of like long run relative frequencies. And you'll often hear this called the random baby problem. By the end of the day today, really by like the middle of the course today, we'll be able to figure out like the theoretical probability distribution here. But since we're thinking about probability as a long run relative frequency, what I'd like to do first is just simulate the process we're interested in, and then we can look at what those long run relative frequencies look like and anticipate what the probabilities are going to be. And the idea of this applet, the idea of this problem is in this case, 4 babies are born in a hospital, and the nurses are not very good, and they just send the babies home randomly with the 4 families that have just given birth. Okay, so this looks like is babies are born, and then the babies go to houses, and if they have a cloud here, that means the baby went to the wrong house, and if it has a sun, it went to the right house. Okay, so kind of a terrifying problem. You can see in this first trial, only one baby went to the right house, the yellow house here. Let's animate it one more time. You see the stork comes. Okay, red baby's going to blue house, yellow, red, blue, green, and none of the babies went to the right house, right? So just in the bottom left here, we're recording 0 matches. Okay, I'll animate it one more time here. Okay, so that time we got two matches. Okay, I'm gonna stop animating it, and I'm gonna ask it to do 1,000 trials. 1,000 trials. So what it's gonna do is just what we've done 3 times, just gonna keep cranking that out 1,000 times here. Okay. Okay, so we can see here, after 1,000 trials, of the 1,003 trials we did, 394 of those had 0 matches. So that's about 0.4, about 40% rather. 317 of them had 1 match. So that's about 31%. 253 had 2 matches, so it's around 25%. None had 3 matches. Why didn't any have 3 matches? Maybe this is obvious, maybe it's not. Why can't you have 3 matches here? Well, because if there's 3 matches, that implies there's a 4th match, right? There's like a degrees of freedom thing here going on. If the blue baby goes to the blue house, the red baby goes to the red house, and the green baby goes to the green house, because there's only 4 babies, we know that the yellow baby must go to the yellow house. So that's why we never have 3 matches here. Okay, and the nurses only got it right. They only got 4 matches, about 4% of the time. And one thing to note here is I can do another 1,000 trials, and these probabilities don't change very much, right? And as I just keep doing it, probabilities aren't changing very much. We say that they've converged to their long run relative frequency. So on the graph at the bottom to the right, it's showing the relative frequency of the relative frequency of zeros. If I click on the 1 bar, it'll show the relative frequency of ones, 1 match. Here it is for 2 matches, and here it is for 4 matches, right? So here's what kind of frequentists are thinking when they talk about probability as a long run relative frequency. They're saying, well, if you repeated the experiment approaching infinity times, the probability would be the relative frequency of that event. Relative frequency of that event. And we can do it with like different numbers of babies, right? So if we do it with 6, okay. Let's take a bet here. If we do it with 6 babies instead, do you think the probability of 0 matches will go up or down? Okay, so we hear up. Others think down. Some think just the same. Okay, so let's note that it's about 0.37 now, about, I guess, 38% now. Let's do it. Okay, so that was one trial. It's not going to be enough. Let's do 1,000. Okay. So it's gone down slightly. It's gone down slightly. Okay, it was about 0.38. I think it's 0.379. Now it's 0.359. And we do silly things like think of that's general. You know, if we do 60 babies, what's going to happen to the probability? Then let's find out. It's still right around 0.37, right? And you know, we haven't done enough trials to know for sure. So we'd really want to do a lot here if we're going to take like kind of this Monte Carlo sort of approach to know whether it's different or not. You know, because it's all right around 0.37. Let's try if we go down. Maybe this one's really obvious. If we only have 2 babies, what happens? 2 babies, they either get them both or get none of them. And the probabilities of no match is about 50%. In general, probability of no matches, I think, goes down a little bit as it increases. But let's find that out theoretically here in a little bit, because, you know, just double check. Let's do 10,000. Yeah, 0.376, 6 babies. 0.37. Again, it looks like it goes down a little bit, but we'll figure out the theoretical quantity here in a minute to like prove that again, because since it's long run relative frequency, you're saying as n increases infinity, n goes to infinity, it'll converge to the probability. The long run relative frequency will conserve to the probability, but any finite sample, we're not sure if it's like, you know, actually converged. Okay. Let's get out of this. Let's get out of that. Whoop. Okay. Okay, so back to the slides here. Yeah, so under this frequency interpretation, we can think if if you roll a die, the probability of getting a 6, just 1/6. Well, the interpretation of that quantity for frequentists would be that the long run relative frequency of 6s when you roll a 6-sided die is 1/6, right? So if we did a similar exercise to what we did with the random babies example, but just with a die roll, in the long run, the relative frequency of 6s should be 1/6. If I flip a coin twice, what's the probability of getting 2 heads? And we can figure this out with that discrete uniform law. There's one way of getting 2 heads, heads, heads. There's 4 possible outcomes: heads, 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 tails, tails, heads, tails, tails. So the probability is 1/4. And again, the interpretation here under this frequentist approach is that if you repeated this experiment, if you flip 2 coins over and over and over again, and each time recorded how many heads you got, 1/4, about 1/4 in any finite sample, but as n approaches infinity, exactly 1/4 would have 2 heads. Probability statements about kind of, I guess, more complex experiments if you want. or so-called natural experiments, if you like, the interpretation can seem a little strange here. So that's why I include it. So under this frequentist interpretation, you might think like, what's the probability it'll rain tomorrow? I think that probability is really low here in Madrid. I don't know, let's say 1% chance. But when we get into interpreting it, how should we interpret that 1% chance of rain here in Madrid in a frequency interpretation of probability? It's going to be just the same as the other two experiments, but it just seems a little weird talking about it. You can think about it as like, if we repeated tomorrow infinite number of times, 1 in 100, 1% of those trials would have rain, right? 1% of those trials would have rain. Kind of the weird thing here is you're like thinking about repeating tomorrow, and in real life, we only get one tomorrow, arguably. So that can cause a little bit of chafing, and some Bayesians will point to that as like one reason that they like that interpretation better. Again, at kind of mathematical level, it's not going to matter for what we're doing today, but I did want to kind of, talk us through some of these interpretations, because they do become really important when you're thinking about how to like interpret statistical results. Okay, so with that in mind, that rain example in mind, if we talk about, and so this is kind of near and dear to my own research interests in political violence, but it also just illustrates kind of a weirdness in thinking about this frequentist interpretation. It's like, if we think about the probability of war between the United States and North Korea in the next year, whatever that probability is, say it's, I don't know, this is hopefully really high, but 5% chance, right? That seems super high, but let's say it's 5%. That's our guess. Well, how would we interpret that? Well, kind of the frequentist interpretation would be that if we repeated the next year over and over and over again, approaching infinity, that the long run relative frequency of those trials would be 5%. Okay. So again, in these sort of like real life events that we don't have like experimental control to like literally repeat, we're kind of appealing to this theoretical idea of like, if we did repeat the next year, how many of those trials would have war? Okay. This is something that especially in studies of like polling that can really get pollsters crossways with the public. It's like, even if their probability estimate's really high of something occurring, that doesn't mean that it will happen with certainty. The syllabus is, I think it's one of the first chats. It's on the website. Perhaps Olga can put it in the chat again. But yeah, there is a syllabus and some recommended reading for kind of each section of the slides here. Thanks, Olga. Yeah, there it is. Okay. So that's just a little bit on interpretation. Let's get back to thinking about random variables and probability here. So again, a random variable is the result of some random process. Usually textbook will call this an experiment, but may more generally just talk about it as a process. And it needs to take at least two different values. Otherwise it's just a constant. So some more examples: number of heads you get in two flips of a fair coin, and take values 0, 1, 2. Random variables are going to be really central to understanding probability and then later statistics. Okay, so to describe the probability, the likelihood, if you like, the likelihood of a variable taking different values, we'll use probability distributions. A probability distribution just gives the possible values of a random variable and the probability of each of those values occurring. So in the discrete case, this is fairly simple, right? So continuing the 2 coin flips example from the previous slide and using that discrete uniform law, we can say the probability of getting 0 heads is 25%. Probability of getting 1 head is 50%. And the probability of getting 2 heads is 25%, right? So if you think about the sample space here, it's tails, tails, heads, tails, tails, heads, heads, heads. Those are the possible outcomes here. And so all we're doing is mapping those outcomes to the random variable and then using this discrete uniform law to assign probabilities, right? Because each of those outcomes is equally likely. That's all we did there. Okay, before getting into the continuous and discrete case further, I wanted to find the cumulative distribution function. And it's a nice time to define it because it's going to have the same definition whether the variable is discrete or continuous. And it's just, so it's usually denoted by a capital F sub x of x, so our random variable's x here. And it just gives the probability that x is less than or equal to some value x, right? So for instance, here's the cumulative distribution function, the CDF, flipping a coin twice, right? So the probability that x is less than 0 is 0, right? So you can see that here. The probability of getting 0 is 0.25, right? We just figured that out here. And so that's why at 0, there's an empty point at 0 and a filled point at 0.25. That just indicates that at 0, the probability of getting less than or equal to 0 is 0.25, right? And in these discrete cases, basically have this kind of stepwise function where, the probability of getting less than 0.5 heads is also 0.25, right? We could get 0 heads, probability that's 0.25. So that's why it's just flat here until we get to 1, and then it jumps to 0.75, okay? Because the probability of getting 1 head is 0.5, probability of 0 heads is 0.25. So just adding those up means the probability of getting 1 or less is 0.75. Okay. And that continues until we get to 2, jumps again, and then it's 1. The probability of getting less than or equal to 2 is 1, right? Because if you flip coin twice, you're going to get 2 or less heads, right? And so, this line really continues to infinity. CDS well defined from negative infinity to positive infinity, but it's just going to stay at 1 here. Just going to stay at 1. Okay, so try this out. It's another discrete one, so it should be fairly easy to just write if in the chat if you like. What's the CDF of the following random variable? The sum of 2 4-sided die. Okay, so probably another opportunity for a D&D joke. I think these tetrahedral die are useful there. But if we take the sum of the 2 4-sided die, what's that CDF look like? Take a minute and try to get at least the first couple elements of the CDF defined, the first couple values. Okay, so one way to think about this is, okay, so the first value we could get is 2, right? So we're rolling 2 4-sided die. The lowest sum we can get is 2. And what's the probability of getting a sum of 2 from rolling the die? Rolling 2 4-sided die. well, you have 4 possible outcomes from each die. The only way you can get it is, the only way you can get it is getting a 1 and a 1. So there's one element that gives you the sum of 2. And so, the next thing is like how many elements are in the sample space. I think you guys can figure that one out. How many elements in our sample space here? So they don't need to be unique. We'll treat one on the first die and then a 2 on the second die. Yeah, 16. Yeah, but because basically by ignoring the uniqueness here, it's going to allow us to use that discrete uniform rule, right? So we can say that the probability of a sum of 2 is 1 out of 16, because there's one way to get it out of 16 possible outcomes in our sample space. But the probability of getting a sum of 3 is 2 out of 16, right? Because we could get a 1 and a 2 or a 2 and a 1, right? So that we get 2 out of 16. And so to define the CDF here, it would just be that the probability of getting less than 2 is 0. Probability of getting between less than 3, greater than or equal to 2 is 1 out of 16. Probability getting between 3 and less than 4 is 3 out of 16, and so on, right? And so we just keep adding the probabilities here. It's going to be a similar stepwise function to this one, but just a little more complicated there. Again, these discrete cases, fairly straightforward here. But let me pause for a moment, sip of coffee, and to see, are there any questions about CDFs? We'll end up using them a bit later. Okay. Okay, so a discrete random variable is one whose possible values form a set of separate numbers that can be listed. Okay. So for instance, the number of heads you get in 2 flips of a fair coin is discrete because it can take a countable set of values, right? 0, 1, or 2. Number of siblings someone has is discrete. You can't have 1.25 siblings. A continuous random variable, on the other hand, is one which can take an infinite number of values along a continuum. Right? These are fairly familiar. So for instance, height, you can be 1.7 meters tall, or 1.700001 meters tall, 1.75 meters tall. The basic test here is between any 2 values, there's an intermediate value. For any values you pick, that implies it's continuous here. Right, so in the case of heights, between any 2 heights you list, I can find another one in between, right? And that's just because it's continuous. Or sorry, that implies it's continuous. This is important because the way in which we deal with discrete variables is going to be a little bit different than the way in which we deal with continuous random variables, right? And I know you guys had a calculus pre-course a little while back. Basically, you can think if we're dealing with continuous random variables, we're going to end up needing to, rather than summing up the probability of each value like we can in the discrete case, instead we're going to need to often anyway use integration to figure out the probability of the random variable falling in some interval. It's just going to be a little bit different here. And so this is around where typically most textbooks kind of split off into the discrete and continuous case, although some definitions, just sort of freely apply to both cases. Again, like the definition of CDF, right? That applies whether or not it's continuous or discrete. Okay. For a discrete variable, if we want to define a function to describe the probability of different values, we can use the probability mass function, which is just going to give the probability that the random variable takes each particular value. Okay, so here, probability y equal y just denotes the probability of a possible outcome value of y. If that function is defined for all values of y, then we have a probability mass function as long as it fits the algorithm, the axioms we defined earlier, right? So in particular, the probability of each outcome needs to be between 0 and 1 inclusive. Sorry, the probability of each, well, I'll just say outcome. The probability of each value of the random variable, say that, is between 0 and 1. And the sum of the probability of all possible values of the random variable. Again, so a little sloppy here. Outcomes, the way we defined it before, it's a little strange here. So think about it as values of the random variable. The sum of the probability of all possible values of the random variable. I suppose, taking a step back and as an aside, when you define a random variable, you're also defining a new sample space on that random variable. So if we think about that new sample space defined by a random variable, then these two statements are just fine as is. We think about them as outcomes of the random variable. So just a little kind of technical note there. Thinking about the two sample spaces can get a little confusing. So I would just think about it as the probability of possible values of all possible values of the random variable, although it's going to be equivalent here. Okay, so a quick example, just to make sure you guys are tracking with this. So figure out the PMF, the probability mass function of how many heads you get in 3 coin flips. And you can use that discrete uniform rule. Again, you just need to figure out the sample space of 3 coin flips and how that maps on to the random variable. And then use that discrete uniform rule to figure out the probability of each value of the random variable. Yeah, so how big's the sample space here? I think that's what Study Up and saying is like, are there 7 elements here? What do you guys think? Do you find 7 as well? Someone says 8, someone says 6. Let's think through it. So we can get tails, tails, tails. We can get tails, heads, 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 tails, 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 heads, heads, right? So there's 3 ways to get, sorry, I'm getting mixed up here. There's 1 way to get 0 heads, all tails. So that's the first element. Where am I? Yeah, there's going to be 8. Yeah, tails, tails, tails. We could get, and then think about for 1 heads, it could be heads, tails, 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 heads, tails, 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 heads. So that's 3. So now we're at 4. Then for getting 2 heads, we could get that 3 different ways, right? So tails, heads, 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 tails, heads, 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 tails. So that gives us 7. And then the last one is 3 heads, right? 3 heads, 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 heads. Yeah, so the order, yeah, so the order doesn't matter for the random variable, but it does matter for how many different ways there are to get each value of the random variable, right? So for instance, to get 0 heads, there's only one way to do it. Tails, 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 right? And there's 8 possible outcomes. So that means the probability of getting the probability of getting 0 heads is 1/8. What's the probability for 1 head going to be? Well, there's 3 different ways to get it. There's 8 different outcomes in the sample space, so it's just going to be 3/8, right? Same for 2 heads. There's 3 ways to get it out of 8 possible outcomes. And then finally, for 3 heads, there's only one way to get that. So it's only going to be 1/8 probability, right? So while the order doesn't matter, so Ibrahim, in response to you, while the order doesn't matter for the value of the random variable, it does matter for the underlying sample space that we're using that discrete uniform law to figure out the probabilities for. That's right. Does that make sense? Ibrahim, do you have any other questions about that? I just want to make sure that's sort of clear here. Drink a little water. Awesome. Okay. Let's see. So if you got a question saying like, is this a proper probability distribution? All that means is, does it conform to the axioms of probability? And so basically in the discrete case, we want to check, are all the probabilities non-negative? Check. I mean, we just enumerated them, right? They're non-negative. And then the other condition to check is that the total sample space of the random variable here, or the, put another way, the sum of the probabilities of all values of the random variable sums to 1, right? So we just figured out that the probability of getting no heads is 1/8, probability of getting 1 is 3/8, so it gets us to 4/8. Probability of 2 heads, 3/8, so it gets us to 7/8. Probability of 3 heads is 1/8, so that gets us to 1, right? So the probability of all values of the random variable summed together is 1. So check, we have a proper probability distribution here. Technically we'd want to show that last axiom satisfied. That's fairly simple to do here, because indeed each of the values of a random variable is disjoint, by the way we defined it. Okay. Okay, so that's for discrete random variables. We'll play around with those a lot, but before we do that, I want to just define continuous probability distributions. Think about them a little bit. So for a continuous random variable, we really can't talk about the probability of getting a specific value. Especially if we think about this uniform law, like think about like the continuous case of that. Well, we have some, for like one event, it's not going to work. One specific value is not going to work because we have a infinite set of potential outcomes. So at that kind of sample space level, technically the probability of like one specific value is 0, right? So we can think like the probability of someone's height being exactly 1.723145829 meters tall is technically 0. It's a set of measure 0, if you like. I don't want to get too much into like measure theory today, but that's sort of the I guess formal way to say it. And so what we're going to do instead is assign probabilities to intervals of numbers. And here, if we assign it to intervals of values, then things work just fine. We don't have this set of measure 0 problem. So for instance, we'll talk about like the probability of someone's height being between 1 and 2 meters. It's probably pretty high. So then a continuous probability distribution is going to be a curve. And the area under the curve describes the probability of the random variable taking those values. Okay. Again, keeping with our axioms of probability, they're going to imply two rules that all continuous probability distributions, or you'll see these referred to as PDFs, need to follow. Okay, the first is they must be non-negative. Okay, so that curve's never going to dip below 0. And the second is that the total area under the curve. So again, if you integrate the PDF from negative infinity to positive infinity, then the total area under the curve has the equals 1, right? And this is just like that second axiom of probability, just in the continuous case. Okay, so to formally define a PDF, a continuous probability density function, recall the definition of a CDF, and that's going to be helpful to us here. So a CDF, a cumulative distribution function, is just the probability that x is less than some value. Okay, so a random variable x is continuous if there exists a function f of x, which is going to end up being the PDF here, such that it's non-negative. It integrates to 1, you know, if you go from negative infinity to positive infinity. And for every a less than b, the probability of x being between a and b is equal to the integral of f of x from a to b, right? And this is just what I had on the last slide, basically, that says that the PDF is going to give the probability of x being in some interval, right? And it's just going to be the area under the curve in that interval. We call this function the probability density function. Like I said, we can define it as the function that satisfies the following. Basically, it's the function that satisfies the definition of the CDF, right? So the PDF, it must be the case that the PDF is, if we take the integral of the PDF from negative infinity to x, it's going to give us the CDF of f of x, right? That's a, you know, really that's the requirement here that makes basically our PDF unique to the random variable. Well, sorry, that's the requirement that makes each random variable have only, you know, just one PDF here. And for technical reasons, this only holds for all x at which f of x is differentiable. So if you think you have, you know, some weird kind of mixture distribution where there's a jump, you know, or some stepwise distribution that's, you know, not fully continuous, then at those sort of like points, things can break down. That's going to be important in some like very technical problems, but don't want to get into it today. In general, you can think of just, you know, the PDF satisfying this definition of a CDF. And that should be sufficient here. Really not too many applications where this differentiability problem gets you in too much trouble. Okay, so just to illustrate kind of the idea here, like if we want to find the probability y is between 0. Yeah, it's a set of measure 0. That's true. Set of measure 0. Thanks, Jishan. Thank you. Yeah, so if we want to find the probability y is between 0 and 1, you know, we just find the area under the curve over this interval, and I just used R here to tell me it's about 34%, right? If we want to find the probability Y's between 1 and 2, then it's just this green area, 0.13. Area of a point, 0 in space. Yeah, good point. Okay. So that's for the normal distribution, right? Which is going to be, a really useful distribution because, well, for a variety of reasons. One place you see it, or you may have seen it before, is with the central limit theorem, right? So anytime you're dealing with the sum or the average of a bunch of independent, identically distributed random variables, that the distribution of that transformation can be approximated with a normal distribution, which I think we'll get a little bit to sampling distributions today. We'll see, how that can be helpful for thinking about, for instance, estimators. But yeah, the normal distribution pops up all over the place. Another example. So the unit continuous uniform here is really simple distribution to find area under the curve because it's just a square, right? So the probability Y is between 0.5 and 1. Well, we just find the area under the curve over that interval, and it's going to be 0.5, right? 0.5. We know the total area is 1. Half of it's going to be 0.5. Why I say it's simple, it's like, okay, if I asked you, what's the probability that Y is between 0 and 0.1? What would you say? Well, you'd say it's just 0.1, right? That area is going to be 0.1. You're just dealing with a square here, so it's pretty simple. It's just the upper bound minus the lower bound. So the probability Y is between 0.7 and 0.5 is 0.2. Okay, one thing to point out, this is going to be really, potentially can be very useful, is that CDFs and PDFs or PMFs for that matter contain the same information, right? And that may or may not be obvious, but that's going to imply that we can work with whichever is easier. There's going to be situations where it's easier to characterize the CDF in like a closed form solution than the PDF or vice versa. And you can do things like calculate probabilities from a CDF fairly easily. So for instance, if we want to know the probability that X is between A and B, well, it's just the CDF of X evaluated at B minus the CDF of X evaluated at A, right? So that can be a really useful fact, Do it on time here. Okay, so that's univariate distributions. Basically, what I want to do next is talk about joint distributions and then a little bit about conditional probability. And then we should be around noon then, and we'll take a break and then come back and talk about expected value and variance. Okay. So the joint mass function, so like the bivariate distribution in the discrete case, often denoted as f of x intersection y, or probability of x equaling x, y equaling y. To save on notation, often you'll see it's f of x comma y. And it's just simply the probability that x equals x and y equals y. Okay, so for example, here's a joint mass function for two random variables. And each variable can either be 0 or 1. And the interior cells here are giving basically the joint mass function. So probability of x equals 0 and y equals 0 is 1/9. The probability of x equals 0 and y equals 1 is 2/9. Probability of x equals 1, y equals 0 is 2/9, and probability of both variables equaling 1 is 4/9. Okay. On the margins here, so outside of the interior cells, it's giving the marginal mass function, which is simply, so for instance, for x, the marginal mass function for x is just the probability of x equaling x, adding up over all values of y. So for instance, for the marginal mass function of x, probability of x equaling 0 is just 1/9 plus 2/9 equals 1/3. The marginal mass function for x equals 1, 2/3. Okay. For the joint mass function, is this a proper probability distribution? Well, certainly all the probabilities are non-negative, so check there. And then secondly, if we add up the probabilities, it sums to 1, right? As Simaba says, like 1/9 plus 2/9 plus 2/9 plus 4/9 sums to 1. Check. We're proper probability distribution. What about the two marginal distributions here, the marginal mass functions? So you're less adding to figure these out. Just marginal distribution for x, well, it's just 1/3 plus 2/3 sums to 1. They're all non-negative. Same deal for the marginal distribution of y. Okay, 1/3 plus 2/3. Okay, so that's the discrete case. Let's talk about the continuous case. So the continuous case is just going to be, again, we'll note as f of x comma y. It's just the joint distribution of x and y. Oops, sorry, I still have the discrete example there. Ignore that. Ignore the table here. Sorry about that. So f of x, y is going to be greater than or equal to 0 for all x and y, and the integral with so if you integrate with respect to both x and y over all values, it equals 1. Okay, so again, we're fulfilling those axioms. Sorry, this table's here. That's obviously discrete. Ignore that. We'll talk about a continuous case here in a minute. For the marginal density function, it's going to be really similar in some ways to the discrete case where to get the marginal distribution of x, we summed up over all values of y. Here, to get the marginal density function for x, we're going to integrate f of x, y over all values of y. Sorry, we're going to integrate f of x, y with respect to y over all values of y. Okay, that's what I have on this last line. Okay, so a few exercises here. We have a little time. Let me just check. Yeah, we have a little time. So say we have x. X is probability of x equals 2 and 3 is 1/5, and probability of x equals 5 is 3/5. Okay, so I'm just defining the PDF there. Hi, Marta. And the question is to plot the CDF. Okay. Okay, so try to plot that CDF. I think probably going to do it pretty quick by now. I'll, where'd my little pen go? I'll write it here while you're working. Well, sorry, I got a little lost on the iPad. I'll fix that in the break. So if we want the CDF here, what oh, here we go, clear. If we want the CDF here, it's gonna look something like if we have 0. Sorry, this is gonna be not the best. X equals 2, X equals 3, and go out a little more, 5. Right, so if we want the CDF here, let me change colors. Well, what's the CDF going to be for all values less than 2? It's going to be 0. Great. Thanks, David. It's going to be 0. And then at 2, it'll be at 1/5. Right, so it'll be a closed dot here, right? Because at 2, it's equal to 1/5. All the way up until we get to 3. And then it's going to jump another 1/5 here. It'll go all the way until we get to 5. And at 5, it's going to jump to 1. Let's define this as 1. And then it continues to infinity, right? So that's what the CDF would look like here. Just as a little exercise. Not sure why it's not clearing. Just do it like that. Okay. Let's stop annotating. Okay, how about this one? So suppose we first flip a coin once, and let's let x equal the number of heads that we get. It's going to be 0 or 1. If x equals 0, roll a, sorry about the typo there, roll a 4-sided die. If x equals 1, roll a 6-sided die. Y is the number that shows on the die. Okay, so here we have a joint distribution, right? We just talked about those. We have a joint distribution here. There we go. We have a joint distribution here. I'd like for you to try to find that joint distribution as well as the marginal distribution for x and y. Okay, so really similar exercise to what we had on this slide here, right? So we want to find the joint distribution in these interior cells and then try to find the marginal mass function by summing up over the values. Okay, so let me put the problem up. Okay. Okay, so how's this going to look like? Well, it's going to look like, let's see if I can get the iPad going. Yeah, there we go. So how's this going to look like? Well, x can either be 0 or 1. And then what are the possible values of y? Well, for y, can either be a 4-sided die or a 6-sided die, right? So possible values are going to be 1 through 6. 1, 2, 3, 4, 5, 6. Okay. So I'm just going to focus on the joint distribution for now. Then we can think about the marginal one here in a second. Okay, so to get the joint distribution here, we can think about each of the following. So if x equals 0, okay, we roll a 4-sided die. Okay, so for this top row, what's the probability of y equaling 1 if x equals 0? So we roll a 0, we roll a 4-sided die after that. Question is, what's the probability of, when you think about, yeah, it's going to be, the joint probability of that is going to be 1/8, right? Because there's 4-sided die, so 4 sides, and a 1/2 probability that we get a tails and get 0. As we'll see here in a minute, because these are statistically independent, their joint probability is just the product of the two probabilities. No, we haven't covered that yet, but as folks are, so Ahmed's basically giving the marginal probability, which I was a little imprecise in what I was asking. Actually, sort of what I'd said is like, yeah, conditional on x equaling 0. What's the probability of y equaling 1? It's 1/4, as Ahmed says, and the joint probability, as Silavo says, is 1/8, right? It's just 1/2 times 1/4, right? So I'll write it here, 1/8. Okay, and that's going to be the case for 1, 2, 3, and 4. Right, 1/8, 1/8. What about the joint probability of x equals 0, y equals 5? Yeah, 0, right? 4-sided die, not going to get no 5s off that. Same deal for 6, right? How about the joint probability of x equal 1 and y equal 1? So remember, if we get x equal 1, we're going to roll a 6-sided die. So really similar to before, to get the joint probability, it's going to be the 1/6 probability. We get a 1 on that die times the 1/2 that and as you guys are identifying, times that 1/2 that we get heads. So it's 1/12. Very good. Okay, so that's the joint probability mass function here. So yeah, not too pretty here, but basically the first 4 column, the first 4 cells on the top row are 1/8. The x equals 0, y equal 5 is 0. Same with x equals 0, y equals 6. And then on the bottom row there, it's all 1/12, all 1/12. Okay. Great. So that's the joint probability distribution. How about the marginal distribution for x? So what's the marginal distribution for x? And again, to do that, we're just going to take the probability of x summed up over all values of y. So for instance, the probability x equals 0 summed up over all values of y. And as you and probably a lot of you who are familiar with coins, know the probability of heads and probability of tails. So probability of 0, 1, and 0 are each 1/2, right? So 1/8 plus 1/8 plus 1/8 plus 1/8. So 4/8, 1/2, and then 6/12 in the lower row there, 1/2 and 1/2. The marginal distribution of y is slightly more interesting, I think. What's that look like? What's the marginal distribution of y here? Yeah. So Agnes, let's return to that in just a minute. I forgot about that question, but should be pretty easy to figure out here in just a second. Well, how about this marginal distribution? Like for instance, what's the probability y equals 1 summed up over all values of x? Well, it's going to be an eighth plus a 12th, right? 1/8 plus 1/12. So I guess 3 24ths plus 2 24ths, so 5 24ths. Yeah, how you got it. It's 5 24ths for the first 4, and then 1/12 for 5 and 6. Right, that's the marginal probability distribute. Sorry, the marginal probability mass function for y. Okay, so that's a little bit on joint probability distributions. What we'll do after the break is start thinking about conditional probability distributions. But before we do that, let's return to this problem that we didn't cover on the first bullet point. Let's see if I can just back this up here. Oh my. Clear all drawings. Okay, there we go. Okay, sorry about the delay. So for this CDF, okay, the idea was to first plot it, okay, and we, kind of gave like a really quick drawing of that. I'll make it again here. So let's call this 0. Ooh. Line here, we go 0.2, 0.4, and 1. Okay, so for the PDF, we'd figured out that for 2 and less, or for up until 2, I should say, so an open dot there, it's going to be 0. At 2, it jumps to 0.2. This is 3. It's not really to scale here, but hopefully gives you an idea. And then at 5, it's going to jump to 1. Right, this is that CDF we got from this here problem. Oh, and I see what might be confusing you there, Agnes. So there's a missing less than sign here, right? So we want to use the CDF now to figure out the probability that 2 is between 2 and 4.5, not inclusive. So the probability x is greater than 2 and less than 4.5. And what's that probability here? Again, we can use that trick of subtracting the CDF evaluated at the upper bound minus the CDF at the lower bound. We just have to be a little careful about whether it's inclusive or not here. What probability do you get? Well, in fact, here it won't matter too much, right? Anyway, what's the CDF evaluated at 4.5? Well, it's 2/5, right? 0.4. Yeah, thanks. And what's the CDF evaluated at 2? What's going to be 0.2? So that means the probability that x is between, the probability x is greater than 2 and less than 4.5 is going to be 0.2. It's just the difference there. It's going to be the same for the inclusive example in this particular case, right? So maybe it's fine, but a little bit of a typo on my part, I guess. But how about for this? What's the probability that x is less than or equal to 3, but greater than 0. Well, probability it's less than or equal to 3, but greater than 0 is just 0.4 here. What if I asked instead the probability that it's less than 3? Strictly less than 3. Well, then it'd only be 0.2. Okay, then it'd only be 0.2. So all that to say, you just have to be a little careful here about whether the bounds are inclusive or not when you're dealing, especially when you're dealing with CDFs. And in particular with discrete distributions, it's not going to be such a big deal with continuous distributions because of the set of measure 0 issue. Oh, better clear my annotations here. Okay, so we're right at noon. I believe, we're all entitled to a break now. Let's take 15 minutes, and then we'll come back. In the second half, we'll talk about conditional probability and Bayes' rule, and then we'll talk about expected value and variance, and then finally, time permitting, we'll talk some about descriptive statistics, in particular, thinking about the sampling distribution of descriptive statistics. Depending on timing, we may just kind of get a general idea of that and why it's important, or we may be able to play around with it some. So let's see where we get. Looking forward to seeing you all after the break. Okay, great. So welcome back. I believe my slides should be back up now. Again, so what have we done so far? We talked some about set notation and probability distributions. What I want to do in the second half is keep building on that machinery and talk about conditional probability and some facts about conditional probability, including Bayes' rule. And then we'll talk some about expected value and variance, both conditional and not conditional. And then finally, at the end today, we'll talk some about sampling distributions of descriptive statistics. And that's really going to start point toward, using probability to do inference and to evaluate estimators and stuff like that. So that's where we're headed. Let me get the chat back up here. Okay. Great. So first, just a definition. So the conditional probability of A given B is just given by the probability of the intersection of A and B divided by the probability of B. Okay, that's the definition here. And before we get into Bayes' rule or any of that, I just want to apply that definition to a case. Okay, so keep this formula in mind. That's what we're going to use. We have all the machinery we need to do this now. We have good understanding of joint distributions for the numerator and probability distributions for the denominator. So let's think about an example. It's a fairly famous example. You might have seen it already, but for those that haven't, it's one that I wanted to make sure include, and it sort of pairs well with the Monty Hall discussion, which we'll have here in a moment. So the problem is as follows. Suppose three prisoners, call them A, B, and C, are each on death row. And the governor decides to pardon one prisoner at random, sort of a eccentric governor, I guess. He says, I'm just going to pardon one at random, equal chance of each one getting pardoned. And I'm going to tell the warden, so the guy that runs the jail, tell the warden my choice, but tell him to keep it a secret. Okay, understandably, prisoner A wants to figure out, like, am I getting pardoned or not? You know, only one of us is getting pardoned. Is it me? So we asked the warden, am I going to get pardoned? He says, well, I can't tell you that. And he says, well, okay. Can you tell me anything else? And the warden says, well, I can tell you that prisoner B is for sure going to get executed. Okay. And so the question is, has A learned anything about his probability of being pardoned given the warden's message? And we'll figure it out here in a minute, but suppose that the warden says, no, I didn't communicate any information here. And we can see whether that's true or not. And prisoner A says, well, if prisoner B is getting executed, then that means it's either me or C getting executed, A or C getting executed. So 1/2 probability of each. So my probability of getting pardoned, my belief has gone up, right? It's 1/2 instead of 1/3. That's what the prisoner thinks. Let's use this statement about conditional probability to figure out the probability of A getting pardoned if probability of A getting pardoned given the warden's message. Okay. And if you're interested, the statement of this comes from page 21 of Casella-Berger, 21 and 22. Okay. So to think about this, let's first figure out the probability of the joint probability for the numerator. Okay, so that's going to be the joint probability of, sorry, the last column here really should be, let me annotate it, otherwise it might be confused. Okay, so what do we have here? We have probability that, so really it should be the joint probability that A, yeah, sorry, this is, one second. So this should be the probability of A and W. W here is the warden's message that B, the probability of the message that either B dies or C dies. Okay, so we can think here, if A is pardoned, right, this is a good outcome for A, what's the probability that the warden tells, so we think about the probability that the warden says that B dies. Well, here we have to make an assumption about the warden's behavior. Let's say that if A is being pardoned, he tells that B dies with 1/2 probability and C dies with 1/2 probability. We can relax that here in a minute and see how it changes things. But let's suppose that's the case. And so it means that the joint probability is going to be the 1/3 probability that A is pardoned times the probability that the warden says B dies, which is 1/2. So it's just 1/3 times 1/2. Okay, 1/6. So with 1/6 probability, prisoner A is pardoned and warden says B dies. Again, W here just denotes the warden's message. Okay. There's a 1/6 probability that prisoner A is pardoned, but the warden says that C dies, right? How about if B is the one pardoned? Well, because the warden doesn't want to tell A, whether he's getting pardoned or not, the warden's only option is to say C dies in that case. So that means there's a 1/3 probability that prisoner B is pardoned and the warden says that C dies. It's basically just that 1/3 probability that B was the one randomly chosen to get pardoned times 1, because that's the probability that the warden says C dies if B is the one getting pardoned. Okay. And then finally, what's the joint probability that C is pardoned? Warden says that B dies. Well, it's 1/3 as well by similar logic. Okay. So for the numerator here, we need the probability that A is pardoned and the warden says that B dies. And that's going to be 1/6. That's 1/6 here. And then divide by the the marginal probability that the warden says that B dies. Okay, so it's going to be 1/3 plus 1/6. Right, that's just the probability the warden says that message overall. Okay, so again, the marginal probability of W here. So it's 1/2. It's just a 1/6 plus 1/3. Okay, so that means the conditional probability is 1/3. The conditional probability that A is pardoned, given that the warden said B dies, is 1/3. Okay, 1/3. So questions about that logic? We're going to return to this example. Again, sorry about the typo there, but hopefully it's clear enough. Let me just pause a minute and make sure y'all are tracking. Okay. Great. So we figured out it's 1/3. So the warden's right. He didn't convey any information here in this particular statement of the problem, right? It was 1/3 whenever the governor was picking. The warden said, oh yeah, B is getting executed. A rational A should think that in fact he still has a 1/3 chance. Basically, you know, if the prisoner A thought that it was a 1/2 chance now, basically they're getting confused about the warden's behavior here. Basically, it arises because the warden is never telling A whether or not they got pardoned, which means they have more options of message when A is getting pardoned versus B or C. Okay, and again, in a minute we can change that decision rule. You know, here the decision rule for the warden, we just said, well, just randomize if A is getting pardoned. Just 1/2 probability say B dies, 1/2 probability say C dies. But, you know, we could have the warden have other decision rules, and we'll see how that affects things. Okay. Clear my scribblings here. All right. Okay, so we'll return to this example. That's just a little bit of a warm-up applying this conditional probability definition. You know, it's just the joint probability of A and W divided by the marginal probability of W. Okay, so what I want to talk about next is Bayes' rule. Okay, and this is a way of flipping around conditional probabilities. So if we start with the statement, PA given B is equal to probability of A and B divided by probability of B, which is the rule we just applied. Well, we can multiply B to the other side. That's what I have on the second line here. And there we have that the joint probability A and B is equal to probability of A given B times probability of B. Looks like I have an extra bracket there, but hopefully that's clear. Okay. Now, by symmetry, then we know that the probability of A and B is also equal to the probability of B given A and probability of times probability of A, right? Just applying the same rule here, this time for B given A, and we can find the same equivalence between the joint probability distribution and the conditional probability distribution multiplied by the marginal distribution. Okay, so that's all I did here. And so that means that we can rewrite the probability of A given B as the probability of A and B divided by probability of B, which using this third line here, we can then say is equivalent to the probability of B given A times the probability of A divided by the probability of B. Okay. And this can be useful because, a lot of times we may be able to figure out the probability of B given A, and we want to use that to infer what the probability of A given B is, right? So for instance, we might know the probability of getting a positive result, given that you have a virus, and then we want to use that to figure out what's the probability I have that virus, given that I had a positive result. Okay. So to think about this marginal probability of B, the overall probability of B, if you like, in the denominator, we can apply the law of total probability. And this is going to be just like when we were talking about joint probability mass functions that we could add up over values of one variable to get the marginal distribution for the other. Okay, so say that events A through K are a partition of our sample space, right? So they're just mutually exclusive events. Then for any event B, the probability of B is just the probability of B given A, I, times probability of AI, summed up for all A, right? That's just going to marginalize out A and give us the probability of B. Okay. And we can just substitute that in the denominator, and then this gives us kind of the canonical statement of Bayes' theorem, which we can then use for all sorts of inference, think about Bayesian statistics, but also just for basically turning around these conditional probability distributions. Again, simple example is you test positive for a virus, the probability of testing positive. If you have the virus, naturally you want to know what's the probability I have the virus given that I tested positive. This sort of problem is very amenable to applying Bayes' theorem. Okay, a little bit of nomenclature here, and this may be familiar to a lot of you. It's like we often call P of A sub I like the prior probability of that event because it's not conditioned on anything, and the probability of AI given B the posterior probability. And the idea is you observe B, so given that B is true, what's the probability of A? You can think of it as updating your beliefs. Given that I saw B, what's the probability of A? Well, that's your posterior, so like your post hoc belief. Whereas probability of A sub I is just the prior belief before you saw B, or unconditional on B. What was your prior belief that A would occur? Okay. A simple example here from coded messages. Okay, so this is pretty general problem, but I'm going to talk about just Morse code because it's really simple. So suppose you're communicating in Morse code, so dots and dashes. And whenever any kind of coded messages are sent, there's sometimes errors in transmission. Particularly something like telegraph lines. There could be wires crossed or some kind of interference, and that means that you're not always going to receive the exact message that was sent. So let's suppose a pretty high error rate for easy math. Let's say that an error occurs with probability 1 out of 10. Okay, so 10% of the time in the long run anyhow, get an error. Let's suppose further that dots and dashes are equally likely to be sent. This isn't exactly accurate. I think, and if you look at like the bulk of Morse code, I think like 4/7 or something is like the actual proportion of dots to dashes. But for easy math, let's just call it 1/2. Let's say they're equally likely. That's our prior belief about the message. Okay, so suppose we receive a dot. We get a dot. And we want to know what's the probability that a dot was sent given that we received a dot. Okay, so take a minute and try to apply Bayes' theorem here to this Morse code problem. And I'll restate it here on this slide. Oops. So the probability that a dot was sent, given that a dot was received, it's just going to be equal to the probability a dot's received, given that a dot was sent. Okay, so that should be 9/10. Times the prior probability a dot was sent, which we said is just 1/2. And then divided by the probability a dot was received. Okay, and again, we're going to use that law of total probability here to figure out the probability a dot was received, which is just simply the probability of receiving a dot given that a dot was sent times the probability prior probability dot was sent plus the probability of receiving a dot if a dash was sent times the probability of receiving a dash. So it's simply going to be 9/10 times 1/2 plus 1/10 times 1/2. Okay. So again, we want to think like, well, what's the probability of A? So probability of receiving a dot, just our prior belief, is 1/2. And what's the probability of A given B? So sorry, probability of B given A. Again, probability that a dot was received given a dot was sent. It's 9/10 because their error rate's 1/10. And then the probability of B, which is this total probability in the denominator. It's going to be 9/10 times 1/2 plus 1/10 times 1/2. So that should be 10/20, which is 1/2. Wait, sorry. 9/10 times 1/2, 9/20 plus 1/10 times 1/2. It's going to be 1/20. So yeah, that gives us 10/20. Okay. Is tracking so far? Anything look wrong? All look okay? So then what's the probability that a dot was sent given that we received a dot? Yeah, it's still 9/10, basically because our prior was equally weighted. Okay, prior was equally weighted. What about if, let me clear this out. what about if instead our prior was that 1/10, yeah, let's keep all tens, 1/10 probability of a dot, 9/10 probability of dashes. What if our language, it was just like a lot more dashes than dots, such that our prior belief was 9/10 that it would be a dash and 1/10 that it would be a dot. Let's keep the same error rate of 1/10. So again, we received a dot. We want to know what's the likelihood a dot was sent. So it's going to be still 9/10, right? Probability of receiving a dot, given that one was sent, still 9/10. But now our prior is going to be 1/10, right? Our prior belief about probability of receiving a dot's only 1/10. And then in the denominator, we want just the probability of B overall. So it's going to be 9/10 times 1/10 plus 1/10 probability 9/10. So some similarity there. Numerator, we get 9/10. Denominator, we get 100. That should be 9/10. Or sorry, 9/100ths. Divided by 18/100ths. In this case, still, let's see, 9/100 divided by 18/100ths. It's 1/2. Thanks, Agnes. Right? Anybody get something different? Do you want me to work through that in like a whiteboard, or is it making sense? Again, I'm just applying the this Bayes rule. The only thing that was different is the priors there. Okay, so sort of a simple example to warm us up, kind of getting used to dealing with Bayes rule for those who haven't before. Let's talk now about a slightly more interesting example, and that's of the Monty Hall problem. Okay, this was a problem that was published in a magazine, I think in the 1970s, and created a big stir. Basically, like the answer the author gave was right, but the reasoning was a little off, so it's created a lot of ambiguity. Really, to like think about this problem carefully, just like the Warden problem, we just have to be really careful about the behavior we posit for, in this case, the game show host. So Monty Hall was a game show in the US in the 70s and 80s. I think it actually continued until mid like 2010s. And there's a little bit of a simplification of the game. They do a bunch of other stuff, guessing prices. So if you know like US game shows, it's kind of like Price is Right. They're showing you, lots of products, try to, prime us to buy stuff. And part of the game is guessing that. I'm going to ignore that. It's not important for the problem. What happens at the end of the game is the game show host shows 3 curtains, and there's prizes behind the curtains. Okay. The prize behind 2 of the curtains is a goat. Okay. Behind the other door is a Cadillac. So, a nice car. Okay. Now, important for this to make sense is that the game show host, Monty, that's his name, hence the name of the problem, he knows what's behind each curtain. Okay. That's going to be important for thinking about the conditional probabilities of what he's going to do coming up. So suppose you pick curtain number 1, okay, and let's assume that the prior probability is that the car is just equally likely to be behind each of the doors, and further, let's assume that you'd rather have a car than the goat. Okay. Now the probability is 1/3 that the car is behind curtain number 1, and 2/3 chance that the goat's there. That's just your prior belief, right? So you picked 1, and then the game show host, Monty, says, okay, behind door number 3, there's a goat, and he shows you that. And then he says, do you want to switch to door number 2 or stay with door number 1? Sorry, I got to switch there. Basically, do you want to switch? And the question is, should you switch or stay? Okay. And we'll derive the probabilities here in just a moment. But what I want to do first is just take an inductive approach and look at an applet that'll simulate this for us. Okay, so it's another one of these Rossmann applets. And it basically gives us the choice of 3 doors. So just like the game show, we pick door number 1, and he shows us a goat behind, in this case, door number 2. And the question is, do we want to stay with door number 1 or switch to door number 3? And before we run this, let me just ask, and whatever the kind of bigger answer is here is what I'll try to choose, or I guess the most voted for answer. Should we stay with door number 1 or switch, do you think? So Fabian says switch. Let's get a few other ideas just to see. Okay, Sarah says stay. I think some people are being slow answering because they're figuring out the conditional probability of the car being behind 1, given that he showed us 2, which is great. Okay, switch or stay. I don't know which to do. I need just a couple more votes. Anybody think it doesn't matter? Elena says switch. Talia saying switch. All right, we got a quorum for switch. Let's just quick switch here. In that case, we lost. Okay, in that case, we lost. That's just one case. Let's reset it. Okay, so that time it didn't go for how we, oh, sorry. Okay, so my record went away, but that's okay. We're gonna do a bunch of trials here. So we switched that time. Let's see how switching performs in like a Monte Carlo sense. What I mean here is if we repeat this process over and over and over again and always play the strategy of switching, how often are we going to win? We know that one time we didn't win, but that's not proof that it's not a better strategy, at least in expectation. So let's first have it do it 10 times. I'll let it animate it so you can get a flavor of what's going on, right? So it's just randomly picking the first door, and then it's just always switching. It's just always switching. Okay, we did it 10 times. We won 7 times. We lost 3 times. Again, probably after only 10 times, we haven't converged to like what the long run relative frequency of winning is for this strategy. So let's have the computer do it 1,000 times. And I'm going to turn off the animation so it'll go a little faster. Okay, so you can see it's just doing the same thing. It's picking a door, and then Monty shows you a goat, and then you switch. And you can see, and now it seems like it's converged. We're right at 2/3, 2/3 chance of winning with this switching strategy. Okay. Can anyone guess what the probability of winning is going to be, the long run relative frequency of winning is going to be with the stay strategy, given that these things are complements? Yeah, it's going to be 1/3, and let's see that. Whoop, I got to reset it. It's mixing strategies. Okay, so it was 2/3 for switching. Oh, I see. It'll keep track of both. That's great. Okay, so if we stay, it's a 1/3 probability. Okay. It's kind of bouncing around a little bit, but should converge to 1/3. Let's get some switches in there too. So the green line here is switching. The blue one is staying. Let me just make them both go far enough. Okay, so we'll figure out what the exact like theoretical probabilities are, but it appears from this Monte Carlo simulation that it's about 2/3 probability winning if you switch and 1/3 probability of winning if you stay. Okay. Kind of a fun thing to play with there. Let's go back to the slides though. Okay, so, this is one of those conditional probability problems that I think illustrates why conditional probability can be a little slippery, and it sort of pushes back on our intuition a little bit. And really the reason why it does that, I think, is because of the game show host strategy. Basically, he's never showing you where the car is, basically. And since he's always showing you a goat that's in one of the doors that you didn't pick, that's going to cause, just like in the 3 prisoners example, a little bit of weirdness in the conditional probabilities. And let's see what I mean by that. Right. So like intuition might tell you like, well, my prior was that that the probability it's behind either of the remaining doors should be equal, but that's incorrect. It's strictly better to switch, like we saw in that applet. And the reason why is Monty knows which curtain the car is behind, and is never showing the car after the first choice. Okay, and we can see what this looks like. So let's think about the host choosing probabilities. So the probability the host chooses door 3, given that the car is behind door number 1. Okay. Well, if the car is behind door number 1, okay, and so suppose we chose door number 1 here. Okay. So if we chose door number 1 and the car is behind door number 1, Monty can show door number 2 or 3. Doesn't matter, right? So let's say he just mixes 50-50, 1/2 probability of choosing door number 3, the host showing us a goat behind door number 3 when the car is behind door number 1. Okay, how about the probability that the host would show us goat behind door number 3, given that the car is behind 2? Well, remember, Monty's not going to show us the car. He's not going to open up door number 2, right? And so that means if we chose door number 1, he's for sure going to show us door number 3 with the goat behind it. Okay. And then finally, what's the probability the host shows us door number 3, given the car's behind door number 3? 0. He never does that. Remember, we've posited he never shows us where the car is. He just shows us a goat behind a door we didn't pick and asks us if we want to switch. Okay, so now we have all the parts we need to apply Bayes' theorem. And again, we want to know what's the probability the car is behind door number 1, given that the host showed me a goat behind door number 3, right? So that's what I have on the left-hand side of this last equation here. And so that's going to be our prior belief or prior probability that the car is behind door number 1. And we said it's just equal behind each of the doors. So it's going to be 1/3 times the probability the host would show us the goat behind door number 3, given that the car is behind door number 1, which is just going to be 1/2. It's going to be 1/2, right? Because he could show us either door number 3 or 2 if the car is behind 1. Okay, so that means the denominator here is 1/6. The numerator here is 1/6. So sorry. The denominator here is going to be the overall probability, the total probability of the host showing door number 3. So it's going to be 1/3 chance that the car's behind door number 1 and times a 1/2 chance that he shows us door 3 in that case. A 1/3 chance it's behind door number 2, and then times 1 because he for sure shows us door number 3 in that instance, and then times 0. 1/3 times 0. So there's 1/3 chance that it's behind door number 3, but he would never show us door number 3 if that was the case. It's 1/3 times 0. I'm just using that same law of total probability to figure out the P of B as a sum of the conditional probability of each event times its prior probability. That's what's going on in the denominator here. Anyhow, that denominator is 1/2. Okay, so we have 1/6 over 1/2, which is just 1/3. So again, a 1/3 probability that the car is behind door number 1, given that he showed us a goat behind door number 3. Okay. So again, this tracks pretty well with what we saw in the applet. Okay, so that's the stay strategy. We would win 1/3 of the time. Let's do the switch strategy. So what's the probability that the car is behind door number 2, given that the host showed us a goat behind door number 3? Okay, so again, we got to figure out these conditional probabilities. Those remain the same, right? The probability of seeing of Monty showing us a goat behind door number 3, given that the car's behind 1 is 1/2. If the car's behind 2, it's 1, and if it's behind 3, it's 0. Okay, so that all remains the same. The prior probabilities remain the same, and our total probability of him showing us a goat behind 3 is also still the same. The only difference here is now we're going to use the prior probability that the car's behind 2, which is 1/3, and the conditional probability of Monty showing us a goat behind 3, given that the car is behind 2, which we figured out above is 1. So here we have 1/3 times 1 divided by 1/2, which is 2/3, right? 2/3. And so here we have theoretical results showing us what we saw in the applet, which is that it is strictly better to switch. We'll do an expectation twice as well. Again, all of this, and the real sort of trick here is this is all predicated on Monty, the game show host's strategy, right? So it's really these first 3 conditional probabilities we figured out given his strategy that are sort of driving everything here. If the host didn't know where the car was, then and just chose at random, then it wouldn't matter whether you switch or stay. It'd also be sort of weird because he'd sometimes accidentally show you where the car is, which never happened in the history of that show, but I suppose one could engineer a game show like that. Okay, so that's the Monty Hall example I wanted to show you guys. Are there any questions about kind of the basic application of Bayes' theorem here, or bigger picture questions about the problem? If not, we'll return to that 3 prisoners problem, which, as some of you probably are already anticipating, is somewhat similar. But I want to make sure and pause and just see, like, if anybody's lost on this, we can play around. Yeah, so it's the ability to switch, Tim. That's really good, right? So the prisoner couldn't switch, right? In a minute, we'll consider, like, well, if the prisoner could switch their fate, would they want to? And as Tim's anticipating, yeah, they would want to, for the same reason here. That's exactly right. That's the difference here, is you can't switch as a prisoner typically, although we'll consider a deal like that and show that, in fact, it becomes a very similar, if not equivalent, although I'd probably argue equivalent problem. Again, really useful discussion here on pages 21 and 22 of Casella-Berger, kind of comparing the 2 problems, but Tim's intuition here is right on. If you can switch, that's like the big difference between the 2 problems. I have another simulation that's on Bayesian search. So this is kind of a cool case of a submarine lost off the coast of the Azores in 1968. And basically, like the way the simulation works is it shows you prior probabilities of each of the sectors based on, whatever information you had at the beginning. And then it has you kind of move around your little destroyer and search for this submarine. Unfortunately, it's not working right now, so we can't play with it now, but I'm going to leave it in the slides. It was working a couple days ago. My guess is their server is just down. But yeah, I recommend playing around with it. Basically, like the problem is like the probability of finding the submarine if it's in the sector is only 0.6. So just because you search it and don't find anything doesn't necessarily mean it's not there. But you can learn from the fact that you searched there and didn't find it. And so it's a simulator kind of giving you the opportunity to do that belief updating. Hopefully it'll be working again in a couple of days. I don't know why it's not working now, but in the interest of time, probably best to skip it anyhow. But I do recommend it. Similar Bayesian search techniques are used for really lots of different applications. I'm sure there's, subtle variations depending on what you're searching for. But, one parallel that the authors make, and there's a nice write-up of the simulator too, and then, that's working, but somehow their simulator's not right now. But in the write-up, they make a parallel to techniques used for the search for the MH370 flight in 2014. So if you're interested in this sort of like Bayesian search where, in particular, it kind of gets interesting when you have multiple sectors and you're updating about all of them at once, I encourage you to play around with it. Again, unfortunately not working right now, but I do think that by skipping it, we'll be able to get into some descriptive statistics and their sampling distributions today. So, okay, so let's consider this prisoner problem one more time before moving on to thinking about expected value. So consider that 3 prisoner problem introduced above. Again, one of them's pardoned, 2 of them are going to get killed. Now, assume instead of telling B or C with equal probability, telling that B or C are going to die with equal probability, which is what we supposed before, is like A is asking, who's going to die of B and C, and he just picks randomly if A is pardoned, right? If they're both going to die. Let's suppose instead that the probability the warden tells A that B dies when A is pardoned is gamma, and the probability that A tells that C dies if A is pardoned is 1 minus gamma, right? So we're just parameterizing that choice. And the question is, for what values is the probability that A is pardoned given that the warden says B less than, equal to, and more than a third? So remember, when it's half and half, we found a third. We're changing the strategy a little bit here to say, well, let's say that they choose he says B with probability gamma and and C with probability 1 minus gamma. And I'm going to go back to that table so that we can just substitute that in. Okay, so remember we had this table. Let's quickly fix this. So remember, this is really the probability of the A and undo NW, or I guess more generally the probability of the decision to pardon that person and the message. Okay, so before, because he was saying with 1/2 probability that B dies when A is pardoned, it was 1/6 was the joint probability, right? The joint probability was just the probability A is pardoned, which is 1/3, times the probability Warden says that B dies, which before was 1/2. Now it's gamma. So, before we got 1/6. What do we get now? Unless I'm mixed up, it should be gamma over 3, right? Because there's a 1/3 chance that A is pardoned times the probability says B dies, which is gamma, right? So gamma over 3. So knowing that, what's the probability then that he says C dies when A is pardoned? Well, it's just going to be the complement. It's going to be 1 minus gamma divided by 3, right? That's the difference in this problem. Okay. What about the probability that he says that? Okay, so we have those two parts. We need the probability that he says that the prisoner is, he says that B dies given that, the joint probability of I'm saying B dies and A getting pardoned. Before that was 1/6. We just figured out it's now gamma divided by 3. I don't know why it's not letting me write. Gamma divided by 3. Oh, I see. So that's the numerator. The denominator is the probability he says that B dies. Probability says that B dies, which is going to be gamma over 3 plus 1/3. Right? Gamma over 3 plus 1/3. Okay, so now we just need to simplify and solve for gamma. That's going to give us, let's first just solve for equal to 1/3. Okay, so here's what the conditional probability is. Try to figure out then what's the value of gamma for it to equal 1/3. Okay, maybe this one's obvious. I don't know. Any questions about the setup here? You guys all right? Well, some of you may have intuited. So before, the decision rule was 1/2, 1/2, basically gamma equals 1/2. And there we got a probability of 1/3. So I think certainly given the setup here, for gamma equals 1/2, it's going to be a probability of 1/3. For what values of gamma is the probability going to be less than 1/3? What do you think? If gamma is less than a half, what do you think that does to the posterior probability? Yeah, so if gamma is greater than a half, what's going to happen? Well, if gamma is greater than a half, and we see it, just put in like, put in 0.5 for, no, sorry, we just did that. Yeah, if gamma is greater than a half, rather than solving for gamma, which what you'd want to do is like solve the inequality, which we could do as well, but just to see it really easily, like plug in 0.7 for gamma. Okay, so if there's a 70% chance, he says B dies whenever A is pardoned. Okay, if that's conditional, then what's that going to do? Well, it's going to be 0.7 times a third. Okay, 0.7 times a third. 7/10 times 1/3. So 7/30. Okay, it's going to be what we plug in and the top. Okay, that's okay. I'm going to show you guys something that'll be helpful for these sort of things. Where is it? Okay. So one way to, I got to turn off the annotation. Sorry about that. One way to show you guys this easily, I think, is if we just go to Wolfram Alpha. Okay, so I'm just going to put in Z for lambda for easy typing. So we got Z divided by 3 in the numerator. Yeah, you guys are working that out. That's cool. All right, Z divided by 3 in the numerator, and let's divide by, we got, so I'm just using Z for lambda for easy typing. Z over 3 plus 1 divided by 3. Okay, if I haven't made any errors here, this should give us the function. Yeah, here we go. So this gives us for, let's say for Z, 0 and 1. Yeah, here we go. So here we go, right? So we can see for 0.5, okay, for 0.5, it was a 1/3 probability, just as we found before. When gamma is less than that, the posterior probability is going to be less, right? And maybe that's intuitive. Like if it's less likely, he tells you that you're going to get pardoned if it's less likely that he tells you B is going to be killed whenever you're getting pardoned compared to him saying C, well, the fact that he told you B is not good news. Oh, I see how you, yeah, you got it. You got it now. Okay, good. Right. Whereas if he's more likely to tell you, so if gamma is more than 0.5, he's more likely to tell you that B is getting killed whenever you're getting pardoned. The fact that he told you that B is getting killed is really good news for you. And so you can see that relationship here. You know, it's nice and monotonic. Maybe that illustrates it a little better than me scribbling here, trying to solve it out with my bad handwriting. Does that make sense to y'all? Do you have any questions about that? Again, just a little bit of a problem to get us going here. Okay, let's go back to the slides then. The annotations messing with it. All right, there we go. Okay. So next we get to this another problem we can think about, let's just have gamma equal 1/2 here. Okay, the special case where he just picks randomly. Suppose A asks if they can switch fates with C after receiving the message from the warden B will die. And the question is to prove it's a favorable change for A, right? That he'd rather be in C's shoes. Again, if B for sure is dying and A is pardoned, happens with 1/3 probability, then the complement is that C is pardoned. That happens with 2/3 probability. So that's one way to prove it. You could also just use the Bayesian updating here. Don't want to show that one out in gory detail. I think you guys can figure that one out. But I think an interesting issue here is based on the warden's strategy. So say we're in this gamma world where, he can choose the probability. He says B dies whenever A is getting pardoned, parameterize that with gamma. When would that be a favorable change for A? And again, I think in the interest of time, let's just look at it graphically and say, well, at 0.5, the probability is 0.33 that A is pardoned. We know B is dying, so that means C is pardoned with probability of 2/3. So when would it be favorable? It's going to be favorable whenever the probability hits 1/2, which basically means he for sure, we can think of it maybe at the limit, but even then, it's always going to be favorable to switch. So here it's 0.5 right at 1. So in that special case, sure, if he's always telling you that B is getting killed, B is getting killed when A is getting pardoned. Well, the fact that he told you is really good evidence that you might want to stay where you're at or at least be indifferent. But that's the only sort of limiting case here. It's going to be strictly better to switch. Again, as Tim points out, like the problem for the prisoner is they're not going to let you switch fates in prison typically. But it does sort of illustrate I think an interesting parallel with the Monty Hall problem. That's why I included here. Okay, so that's what I wanted to cover, thinking about like applications of Bayes' theorem and conditional probability. We'll return to this idea of conditional probability when we talk about conditional expectation. But before we do that, I want to cover statistical independence quickly and then talk about expected value and variance. So that's where we're headed. And again, feel free to ask questions as we're moving through this. Okay, so first, a formal definition of independence is that X and Y are independent if and only if the probability of A and B is equal to the probability of A times the probability of B. Okay. That's equivalent to saying that the probability of A given B is equal to the probability of A. You can prove that with what we've learned so far today, the facts about conditional expectation, but I'll leave that to you. This also implies to be a Bayes rule that the probability of B given A is the probability of B, and will often denote, especially textbooks will often denote statistical independence or the independence of two random variables as A orthogonal to B. So that symbol there you can read as orthogonal, or in a bivariate case, just say perpendicular if you like. It's independent of B. A is independent of B. Independence is sometimes assumed. So, for instance, in statistical models, like when we run a statistical model, we might assume that our observations are independent and identically distributed, right? That's an assumption. But sometimes we'll derive that two variables are independent, or in specific, sometimes we'll show that they're not independent. So, both will happen. I think coming up, I have a couple little examples to show you what I mean there. One point I'll make is disjoint events with a positive probability are not independent. So for instance, if you flip a coin once, the probability of getting heads is not independent of the probability of getting tails, since they're disjoint. I mean, they're also complements, so for sure not independent there. A few properties of independence I want to highlight. If A is independent of B, then the following pairs are also independent. So A and the complement of B, the complement of A and B, the complement of A and the complement of B, and so on. I'm sure you can imagine a few other pairs derived from that. Basically, like if you're independent of a variable, you're independent of its complement. Okay, so let's think about an example here. Suppose we first flip a coin once, and let's let x equal the number of heads. So it's the same distribution, same joint distribution as we saw before. If x equals 0, roll a 4-sided die, a tetrahedral die. If x equals 1, roll a 6-sided die. Okay, roll a 6-sided die. And y is just the number showing on the die. Okay, so earlier we found the joint distribution here, right? So on the top row, if I remember correctly, it was 1/8 for the first 4. So for 1, 2, 3, 4, y equals 1, 2, 3, 4, x equals 0. And then it was 0 for 5 and 6. And then you may remember in the denominator is 1/12 for each cell, all 6 cells down there. So a little bit of orientation there if you need it. Now the question is, are x and y statistically independent? So think about that. Let me know in the chat what you think. Again, definition of independence here is that the probability of A and B is equal to the probability of A times the probability of B. Yeah, they're not independent, right? They're not independent. And the way to find that out is to compare the joint distribution to the probability of A times the probability of B, or probability of X times probability of Y in this case, right? So 1/8 is the probability of getting a 1 and a tails and a 1 on the die. So let's see, that's 1/8 should be 1/2 times 1/4. So that one checks out. However, things start to break down whenever you get out to the cells out to the right-hand side, right? Put another way, the fact that you get a 5, the fact that you get a 5 on the die roll basically tells you for sure that you must have gotten a heads on your coin flip. And so because the probability of, another way to think about it is the conditional probability of heads, given that your die roll is a 5, is not equal to the unconditional probability of just getting heads, right, which is a half. So the conditional probability that you got heads, given that you saw a 5 on your die, is 1, right? And so since those aren't equal, it can't be statistically independent. That's one way to show it here. Again, the fact I'm using there is that the probability of A given B equals probability of A if they're statistically independent. It was really just a restatement of the definition there. Let's clear this out. Yeah, clear all drawings. Whoop. All right, come on. There we go. Still annotating. Sorry, guys. Okay, there we go. Right, so an approach here would be to find the conditional probability that x equals 1 for y equals 1, y equals 4, y equals 5, and then compare that to the unconditional probability. You can also see it if you find the conditional probability that y equals 5 given x equals 1. Okay. I guess we can do these quickly. So what's the conditional probability that x equals 1 if y equals 1? I don't know if that one's obvious. So if we get a 1 on the die roll, what's the conditional probability? All right, I want to make sure and get to expectation. I'm going to leave this one to y'all, but basically you can just apply that definition of conditional probability. Okay, and I believe the slides will be made available to you guys, so you'll see that there's some exercises throughout. Yeah, you're on a good track. Yeah, check that out, and we'll leave these as exercises. I want to make sure and get to expectation. Okay, so just like, think about like the mean of sample data or something like that, probability distributions also have a mean, which we'll refer to as the expected value. Okay. If we think about like for a probability mass function, then it's just going to be the sum. So often you'll see the expected value denoted as mu, or the mean of the probability distribution denoted as mu. And it's just equal to the sum of each value of the random variable weighted by its probability, or times its probability. Okay. Summed up for all values of y. For the continuous case, similar, it's just the integral of y weighted by, it should be f of y dy there. In either case, the expected value is the value that we would get on average over a long sequence of repeated draws from the distribution. So you can think about this as like, if we repeated the process over and over and over again, recorded the value of our random variable each time, and then took the average of those approaching infinity trials, the number we would get would be the expected value. So really simple example is if we flip a coin once and let y be 1 if you get heads and 0 if you get tails. What's the expected value there? I bet a lot of y'all can do this one in your head, right? It's just 0.5, right? It's 1 times 0.5 plus 0 times 0.5, right? We're just taking each value of y and multiplying by the probability that value occurs and summing up. Yeah, thanks for that, David. Exactly right. Okay, how about if y is the number you get on a fair die? So a 6-sided die, equal probability of each face. Yeah, it's going to be 3.5, right? It's just 1 times 1 6, 2 times 1, sorry, 1 times 1 6 plus 2 times 1 6 plus 3 times 1 6 plus 4 times 1 6 plus 5 times 1 6 plus 6 times 1 6. And if you add all that up, you get 3.5. Exactly right. Okay, so one way, for folks who are I know you had like calculus pre-course recently, but just some intuition here is basically you can think about the continuous probability case as being like the average over all values weighting by the height of the probability distribution. That's a little bit of an abuse of nomenclature, but if you need some kind of intuition, that may help you out. So for instance, if f of x equals 1/10 for x in the interval 0 through 10, what's the expected value? What's the expected value there? So it's a really easy integral to do. It's just the continuous uniform here. Because the probability is 0, when you're less than 0 and more than 10, you can just treat the bounds here in the interest of time as 0 and 10. Again, technically to get expectation, you want to go negative to positive infinity, but it's fairly trivial here to show, since there's no probability less than 0 or more than 10, that you can just focus on that interval where there is probability. Okay. So what's the expected value there? Okay, so just in the interest of time, I'm just going to show you graphically. So we have this uniform distribution, minimum of 0, max of 10. So the CDF, so when you do that integral, you should get x over 10, right? The integral of, sorry, for the CDF, if you're just taking the integral, it'd be x over 10. To get the expected value, it should be the integral of x times x over 10, which if you do that integral and solve, you'll get 5. You'll get 5. But that's the basic process here. Again, speeding through a little bit in the interest of time, but since y'all just had a calculus pre-course, I think probably hopefully safe to do so. So again, it's just x times, it's the integral of x times 1 over 10. So x over 10 with respect to x from 0 to 10, that'll give you the expected value. You should get 5. And for the CDF, it's just simply the integral. And again, this Wolfram Alpha site, I really recommend, if you're struggling to figure out some function, you want to see it plotted. It's an easy, quick way to kind of do that. Okay, so that's a little bit about expected value. Next, I want to get into some sort of more interesting rules we can apply. Okay, so the first is the so-called rule of the lazy statistician, and so-called because it really can make your life a lot easier. So say you have some function of y. You have some random variable y, which is a function of a random variable x. Okay, so y equals r of x. Okay. So the expected value of y is going to just be the expected value of that function of x. And so what that means you can do is just take the integral in the continuous case of the function times the probability, the PDF of x with respect to x. And that'll give you the expected value. Okay, so basically what's different here is you're using r of x rather than just putting x in, like we had for the expected value. The discrete case, it's going to be just the sum of rx times f of x, where f of x is just the probability x equals x. So why this is nice is it can be a lot easier than figuring out the probability distribution of some transformation of of X. Sometimes it can be difficult, and in like a mathematical statistics class, one thing you would do is get a lot of practice doing bivariate transformations and showing that the function's one-to-one and onto, so then you can apply theorems and try to figure it out. But in general, it's quite difficult. Whereas if you just need the expected value of some function of X, much easier just to apply this rule. That's why it's called the lazy statistician's rule. It gets you out of figuring out the whole PDF of Y, where Y is some function of X. As a bit of an example, think about if X is a continuous uniform between 0 and 1, and Y is e to the X, okay, e to the X, just a function of X. Well, then we can apply the lazy statistician's rule and say that the expected value of Y is the integral of 0 to 1, the integral evaluated from 0 to 1 with respect to X of e to the X times f of X, okay? And we know for the uniform, the PDF is really simple. It's just 1 over 1 here. So that sort of goes away in a sense. Just multiply e to the X times 1. And then we're left with this integral of e to the X from 0 to 1, which equals e minus 1. So we can say the expected value of Y is e minus 1, even though we didn't find the distribution of e to the X. We didn't find the distribution of Y. We were still able to figure out the expected value of Y. And basically the trick we used was we just used the probability distribution we already knew, the probability distribution of X, and the fact that Y is a function of X. Okay, so really, really helpful tool here. Another fact about expectation I want to highlight, and this one's also helpful, is the linearity of expectation. What I mean by that is the expected value of X times some constant plus some other constant B is simply A times the expected value of X plus constant B, right? So if we multiply by a constant, it's just going to multiply our expected value by that constant. And if we add a constant, it's just going to add it to the expected value. And so this is, again, a nice way we can avoid having to figure out, more complicated probability distributions using the fact that there's linearity in expectation. And this actually derives from the lazy statistician's rule. I have the derivation here. In the interest of time, I'm gonna cruise past that, but that is where if you want to like prove the linearity of expectation, you can prove it with the lazy statistician's rule, and that proves here. Okay, so that's expected value. Let's talk a little bit about variance. So the second moment of a probability distribution is variance. The variance of a probability distribution is the expected squared deviation from the mean. Okay, so you might want to know, like, well, what's the typical value from this distribution? We might also want to know, like, how far should I expect to be off from that typical value? And that's where variance can be helpful. Okay. Standard deviation is just the square root of the variance. Okay, both of these contain the same information, and they're both just measures the spread of a distribution. For calculating the variance, formally it's just the expected, again, the expected difference from the mean, the difference from the expected value squared. Sorry, misspoke. It's the expected squared difference from the mean. Okay, so that square is inside the expectation there. Okay, maybe I'm missing a square bracket. Let's show you what I mean, just to make it really clear, because people get confused there. It's the expected squared difference. Okay. The alternate statement of the variance is the expected value of x squared minus the square of the expected value of x. Okay, so that can be useful whenever, for instance, like getting this expected value is difficult. For some PDFs, it's going to be really gross, that first line. And it can be a lot easier to just find the expected value of x squared and then subtract off the square of the expected value of x. Okay, that can be easier. So it's a useful fact. It's just an alternate statement of the definition with some rearranging. And then, so similar to what I said about, adding and multiplying constants for expected value, we can also think about that for variance. Adding a constant b isn't going to change the variance. However, multiplying by a scalar a constant a, is going to result in the variance being a squared times the variance of x. Okay, a squared times the variance of x. Okay. It's annotation. All right. There all goes. There we go. Okay, so if we want to figure out, for instance, so this example we keep using of just a simple Bernoulli, coin flip. You flip a coin once, let y equal 1 if you get heads, 0 if you get tails. We've talked about probability distribution there and expected value there, found it was 0.5. If we want to find the variance, it would just be the sum of each value minus 0.5, which is mu here, times the probability of that value. There's only two values, so it's pretty simple. It's just 0 minus 0.5 squared times 0.5 plus 1 minus 0.5 squared times 0.5. Right, so the variance here is going to be a quarter. Oh yeah, this is for the discrete case. Continuous case. Just to give you some intuition, I think probably, those who thought about variance before probably really very familiar, but just in case, the red density here has a smaller mean than the blue density. Red density has a larger variance than the blue density. Again, the variance is just a measure of spread here, measure of spread. Okay, so a little bit of summary and then want to do something with all this. So, probability distributions describe the likelihood of a random variable taking different values. For a discrete random variable, the probability distribution, the probability mass function, gives the probability that the random variable takes each possible value. For continuous random variables, the probability distribution gives the probability of the value falling into any interval as the area under the curve over the bounds of that interval. And often we'll use the expected value and the variance to describe distributions. They don't tell you everything about a distribution, but they tell you quite a lot. And as you go along, you'll probably end up talking about moment generating functions. Don't have the time today to talk about that, but there's first moment as mean, second moment variance, and then you have third through infinity moments, right? And characterizing the moments of a distribution can tell you really a lot of information about the distribution itself. And so sometimes, like, for instance, in problems where you want to show two distributions are equivalent, it's not obvious that they are. If it's too hard to derive the PDF, so say you're working from the CDFs or something, then or maybe it's some weird transformation. You want to know, is this transformation equivalent to some distribution I already know a lot about? What you can often do is characterize the moments, the mean and variance and so forth. And if you can show that all moments are the same, and in particular the function generating the moments is the same, then you've proved that those two distributions are the same. So just give you a little bit of, I guess, preface or something, that this idea of moments can be generalized to more moments than just two, and that figuring out the function that the moment generating function can be useful when you get into like more complicated transformations of variables. Okay, so let's see, how are we doing on time? Okay, so I am gonna pass these exercises. I'll leave them in for folks that want more practice. If we have time, let's come back to them. Basically, I just have a couple exercises practicing with expected value and variance. So the first is a simple game. You start with $C. On each play of the game, you either double or half your money with equal probability. So 1/2 chance it doubles, 1/2 chance it halves. And the question is, what's your expected fortune after 2 trials, and what's the variance? Okay, so that's one question. The other question I had is the same deal about flipping a coin once, x equals 0. You roll a 4-sided die, x equals 1. Roll a 6-sided die. Y is the number showing on the die. And it just asks you to find the mean of y and the standard deviation of y. Way to find the standard deviation is just find the variance, take the square root. Anyhow, you have both definitions for the discrete case in the slide, so it's just a matter of applying that to that joint probability distribution that we derived earlier. So you can check that out if you're interested. But I think in the interest of time, we better keep on trucking here. So let's see. So yeah, so that's a little bit about expected value and variance. Next, I want to talk just a little bit about covariance. You can think about covariance as how two variables move with each other, at least on average. So for instance, let x and y be random variables with means mu x and mu y. Again, equivalent to just saying that with expected value mu x and expected value mu y. And they have standard deviations, sigma x and sigma y. Okay, and we wanted to find the covariance between x and y as the expected difference between x and mu x times expected difference between y and mu y. And what this is going to tell you is that whenever x is below its mean, is y also below its mean? When x is below its mean, is y above its mean? You know, are these do these vary in a positive sense or a negative sense? And you can connect this directly to the idea of correlation. You know, are these positively correlated or negatively correlated? And in fact, the correlation is simply the covariance divided by the standard deviation, the product of the standard deviations of each variable. Okay, so that gives us the correlation. Okay, a few properties of covariance that are worth noting. So the covariance of x times y is equal to the expected value of x times y minus the expected value of x times expected value of y. Sorry, there should be a line break here. And that should be x. If x and y are independent, then their covariance is 0, right? Again, you can think like, well, since independence implies that the conditional probability is equal to the just overall probability. So the conditional probability of x given y is equal to the probability of x. Well, then that implies the covariance should be 0, because if it was the case that when x is above its mean, y is also above its mean. That means if I told you the value of y, for instance, if I told you y is above its mean, then the probability of x being above its mean would be greater, which would violate this rule about conditional probabilities. So if they're independent, that implies the covariance is 0. You have to be a little careful. The converse isn't true. So just because the covariance equals 0, that doesn't imply that x and y are independent. So you have to be a little careful about that. Basically, there can be relationships between x and y that aren't linear, and that can cause issues where the variables are dependent on each other, but the covariance equals 0. Generally, the variance of x plus y is equal to the variance of x plus the variance of y plus 2 times the covariance of x and y. Right? So if you want to figure out the variance of a sum, for instance, and the variables aren't necessarily independent, then you can apply this formula. And if you can figure out the covariance, then you can figure out the variance of x plus y. Okay, so it's a little bit on covariance. Thinking about the 2-variable case, I want to comment some on conditional expectation. So in the discrete case, conditional expectation is just the expected value of x given y is how we denote it. So given that y equals y, again, when we're, the typical notation here is like capital Y is denoting a random variable, lowercase y is denoting a particular value of that variable. Okay. Anyway, in the discrete case, it's just the sum of x times the conditional distribution of x given y, and sum up over all values of x there, and that'll give you the expected value of x. So it's really similar to the expected value equation generally. The big difference here is that you're using the conditional distribution of x, the distribution of x given y. That's the big difference here. Same in the continuous case. Continuous case is going to be the integral of x times f of x given y dx. That's the how you find expected values, conditional expected values. So for instance, if you think about that case from before of flipping a coin and then rolling either a 4-sided or a 6-sided die, well, you think about the expected value of y given that x equals 0. Well, that's going to be the expected value of a 4-sided die, right? I think it should be 2.5. Whereas the expected value given that x equals 1, so given that you got a heads and rolled the 6-sided die, the expected value of y is going to be 3.5, right? Because it's a 3-sided die. Or it's 3-sided, a 6-sided die. 3-sided die would be tricky. I mean, I guess a 2-sided die is like a coin. 3-sided die is a little weird. But a 6-sided die is 3.5, as David pointed out. One rule to note here is the rule of iterated expectations. So if you want to know the expected value of y given x, the expected value of the expected value of y given x, it's just going to be the expected value of y. Basically, you're by having the two expectations, you're just integrating over all those values of x, and that just leaves you with the distribution of y, which then leads you to the expected value of y. Okay, so have a couple exercises here. So this is, oh, nice. Okay, so I have that same example with the 4-sided and 6-sided die. Again, if you get a tails, roll the 4-sided die. If you get a heads, roll the 6-sided die. And so then a question is like, what's the covariance of X and Y? And the correlation. So again, to figure that out, you just apply that covariance equation for each value of X and Y, and sum up, and that should give you the covariance, right? So it's the expected value, so it's going to be the sum of that stuff. Oops. Okay, so that's something you can practice if you like. Again, running out of time, and I want to talk some about descriptive statistics before we stop here. Correlation, you just divide by the standard deviation of X and Y. So again, you'd have to figure out the standard deviation, which we already figured out the variance, I think. So just take the square root. And then based on these results, are X and Y statistically independent? So again, you can use this fact about the covariance. If they're independent, the covariance equals 0. So a little bit of a spoiler, you'll find the covariance not equal to 0, therefore they can't be independent. Again, you do have some things that covariance is equal to 0, but they're dependent. But if your covariance is not equal to 0, then they're definitely dependent. So you can be in good shape there. And then some practice finding the conditional expected value. This is kind of what I was going through quickly, just in words. It's just like, what's the conditional expected value and variance of Y given that X equals 1 or X equals 0? And, for that, I would just look at the slides and also look at either the Wasserman or the Casella-Berger book, and you should be able to figure it out if you look at the sections that I indicated there. Again, just kind of to make sure you're tracking with this. And really, really simple example, but working through these simple examples can help when you get to more complicated ones. So I recommend that. Unfortunately, we won't have time to go through these exercises together here, but I am confident that you should be able to figure them out between yourselves. Yeah, feel free to reach out via email as well. If you Google me, I'm sure you'll find me. So happy to take some questions over email. That's just fine. Okay. So if you get the first conditional expected value of Y given X equals 1 and X equals 0, go ahead and do it for the conditional expected value of X given that Y equals 4 and Y equals 6. Okay. That'll just give you some practice with dealing with conditional expected value. I'm realizing in the slides I didn't go through conditional variance. Again, in Wasserman or in Casella-Berger, the definition's there. It should hopefully be somewhat intuitive if you feel confident about conditional expectation. So take a look at that. But yeah, I'm realizing that's not in the slides here. So if the part about conditional variance is confusing, that's why. Just go ahead and look at the definition probably in Wasserman's going to be the best text to look at, and then try to apply it in this particular example. That's what I would recommend. Okay, so we have about 15 minutes left together. I want to talk a little bit about descriptive statistics. And whenever I teach like my undergraduates, usually one of the earlier things we talk about is descriptive statistics. I figured you guys are more advanced. We don't need to like go through all these different types of descriptive statistics. I think a lot of them will be fairly familiar. But what I do want to talk about is the idea that descriptive statistics, and in particular, statistics derived from, for instance, a random sample, are going to vary under repeated sampling. There's going to be variability, right? And one easy way to see this is, suppose you're interested in the attitudes of people in Spain about free trade with China. Okay, just like a policy thing you're interested in. So you call 100 people in Spain, randomly selected, and you get the proportion of people who favor free trade with China. You just call them up, you ask, hey, do you favor free trade with China? Yes or no? Okay, so you get a proportion, I don't know, say it's 50%. Okay, so half of the 100 people you talked to said they favored free trade with China. If you called another 100 randomly selected people, do you think you're going to get 50% again as your sample proportion? So to be clear, the sample statistic here is the sample proportion, the proportion of people in your sample that said they favor free trade with China. So you got 50% the first sample of 100. If you take another random sample of 100 people, do you think you'll get exactly 50% again? Well, likely not. One person says 50%, but think about it. I mean, so 50 of the 100 people you called said they favored. But if you call another 100 people, you might get 49, right? Could happen. Or you might get 55, right? You're going to have some variability under repeated sampling. It's certainly possible you get the exact same number again, but it could vary, right? And if you're trying to use that sample proportion to estimate, for instance, the actual proportion of people in Spain that favor free trade with China, well, it really matters whether that sample proportion, each time you do it, if you did repeated sampling, I mean, if it's going to be like exactly the same every time. Like, so for instance, you do the study once, you get 49%. Next time you get 50%. Next time you get 51%. Next time you get 49%, right? There's some variability, but it's all kind of around the same place. You can be a lot more confident in your estimate in that case than in the case of the following. Say you do the study once, you get 50%. You do it again, you get 20% support. You do it again, you get 80%. Do it again, you get 10%, right? Your estimates are all over the place. And so that means you really shouldn't be that confident that any particular estimates, reflecting it's serving as a good estimate as of the sample proportion, right? You want estimators that under repeated sampling don't vary very much, conditional on them being unbiased, which is a question about the expected value of the sampling distribution. Anyway, all that's just a little bit of a long example to point out that the variability of your descriptive statistics, your sample statistics under repeated sampling, is paramount to evaluating the quality of your estimators. So let's get into that, right? So we want to calculate statistics. These are just numbers calculated from data. And often we're using the statistic as an estimator, right? We're using it as an estimator. We're trying to make a guess about some unknown parameter. For instance, the proportion of people in Spain that support free trade with China. We want to estimate that by calling up 100 randomly selected people and using the sample proportion as a guess. Okay, and we want to know how are our guesses going to perform in the long run? Like, if we use this procedure to calculate our estimate from our data, should we expect to be close to the true population proportion or not? right? That's kind of paramount to what we want to know. And that's a question about how statistics vary under repeated sampling. Okay. And this points out that descriptive statistics under repeated sampling have distributions, and to evaluate estimators, we need to understand those distributions. Okay, I'm abstracting away from a lot of things you might wonder about with sampling and all of that. Just think about a random sample. If you have some other sampling structure, you'd want to reflect that in your sampling distribution. Gonna not talk about that today. That's something you'd probably talk about in like a survey research course. That'd be a big thing to pay attention to. But a statistic's just a numerical summary of a sample. And again, for this discussion, let's just assume random sampling. It's going to be kind of the simplest case to talk about here. And so therefore, for a given data set, statistic just has one single value, right? So if we pull 100 people and ask their income, they say 50K USD, the average of what they say. So you add up everybody's incomes and divide by 100, you get 50K. That's the average, the average income in your sample. But we can also think about how a statistic would behave under repeated sampling. And that's going to tell us a lot about whether that 50K or sample mean is a good guess for the actual, population average income, right? So if we know the population distribution of income, what's going to happen if we randomly select 100 people and average up their incomes? There's a nice applet we can use to think about this a bit. Okay, this is the last one, I promise. Okay, so say our income distribution, something like this. Okay, this is our income distribution. It's skewed. There's some people making a lot of money and a lot making less. Okay, the average is, in this case, 8. I guess we think about it as like 8,000. Median is 7. And so the idea is, if we're going to take a sample of, let's do a decent sized sample, let's say 20 people from this distribution and get the average. How's it going to look like under repeated sampling? So first, let's do it once. Okay, so we're going to take 20 people. I won't animate all of them, or it'll take a while, but the idea is we take 20 people. We got one really rich guy and everybody else kind of lower down. Anyway, we've got a mean here. Think of around 8. Okay, let's do it again. Okay, so again, if we take another sample, we're going to take another 20 individuals from this population on the first row. If we do that, are we going to get exactly the same value again? What do you think? Yeah, it's possible. Lena's right, it's possible. But Virginia also has a point, like probably not. There's some variability. Probably not. It's certainly possible. Let's see. It could happen. Let's see. Right. And the reason why is because our sample's random, right? Our sample's random. And so therefore the value of the statistics random. And in fact, it was a little less. So it looks like this time we got 8. I guess the last time we must have got 9. Because the average of our 2 repetitions is 8.5. Okay, so I'll animate it one more time, and then we'll do kind of full Monte Carlo and take a bunch of samples here. Okay, we did it again. In fact, we got the same. Between 3 and 2, we got the same average, right? We have 2 blocks there. All right, let's do it 5 times. Not going to animate. It's just going to plot the means. Okay, do it 5 more. Let's do it 10,000 times. Okay, 10,000 more. All right, we're at like 100,000. I've clicked, I guess, 10 times. A little more than 100,000. What we can see is the distribution is not changing very much. It's not changing very much. And it's centered around the population mean, which is good. It means our estimator's unbiased. And expectation, or expected value of our mean, is the population mean. It's good. We probably wouldn't want to use a estimator that's on average, different from the population mean, although there are some reasons one might do that. And we can also notice like the standard deviation is a lot less. Standard deviation is a lot less than our population standard deviation. So here it's 1.39, 1.39 rather than 6.22, which is our population. Let's compare two. I'm going to keep 20 in this second to last row. And then in the last row, let's do a smaller sample of 5. Which of the two sampling distributions, again, the distribution of the sample means under repeated sampling, which do you think is going to be more variable? And I'll animate the first set here to just give you an idea of what's going on, right? So we're going to take 20 and take the mean. Okay, 20, plot the mean. Now it's taking 5 and plotting the mean of those 5, right? Which of these two distributions do you think is going to have a higher variance? We'll animate it one more time. What do you think? Yeah, n equal 5 is going to have a lot more variance. It's going to be a lot more variable because we have a lot less information from the population. Very, very good. Very good. Let's see. So let's do 10,000, 100,000. Again, after, as the number of repetitions approaches infinity, these distributions converge to the theoretical sampling distribution. I think we're at like 5 million, 5.5 million now. So that's hopefully enough. And we can see that, again, the standard deviation, both are centered at 8.08. So that's good, unbiased. However, the standard deviation when n equals 20 is a lot less than when n equals 5, right? N equals 5, it's 2.78. That's more than, well, it's about basically double what it is for n equals 20. Okay, so just an applet there, something that's kind of nice to think about repeated sampling and this idea of sampling distributions. You can change up the population distribution, whatever you want, and play around with it. Kind of interesting. But basically the point for today is just to introduce the idea of a sampling distribution. And that's just the distribution of the values a statistic can take under repeated sampling. Okay. And it turns out we can characterize, just with what you learned today, and we won't fully do it, but it's in the slides, that the sample mean has a mean of mu and a variance of sigma squared divided by n, where sigma squared is the population variance. And we can actually figure that out without, approximating with normal distribution or anything like that. We can just use basically the linearity of expectation and the latency statistician's rule to show that the expected value is equal to the population mean mu. For any random sample where the population has a finite variance. If the variance is infinite, something like Cauchy distribution, this won't apply, but for anything else, you can show that. This isn't going to tell us the whole distribution. It's not going to tell us the whole distribution, but it is a lot of information, to figure out, the probability our mean is, in a certain range, then we'd have to figure out the whole, sampling distribution, or at least an approximation to it. And that's where central limit theorem comes in. But to show that the expected value is equal to the population mean, you have enough probability skills just from today to do that. And again, the Wasserman text has a nice proof of that. I basically summarize it here. Same deal with variance. We can use the facts we know about variance to show that the sorry, that E should not be there. The variance is already an expectation. So the variance of Y bar is equal to the population variance divided by the sample size. And, you know, we can see that in the applet as well. So the population variance there, I think, was 36. Let's see. It's worth looking at. Go back to our skewed distribution. Okay, so if we do this again, we can see that our population variance is about 36, and our variance of our sampling distribution is just that 36 divided by our sample size at 20, and then take the square root because it's giving us the standard deviation here. Okay, so anyway, just something to kind of plug here, since you should have enough facts now to see that yourselves. So I encourage you to do that. You can kind of see this behavior from this figure. So, you know, 1 draw is just the population. Mean of 10 draws, you can see the variance gets smaller. Mean of 100 draws, you can see the variance is much smaller relative to the population. I have a couple examples there. We won't have time to go through. We're hitting time here. But check those out to learn more about sampling distributions. And then I have just a little bit on the central limit theorem, but you know, don't prove it or anything. I also linked to a YouTube video that's sort of interesting, talking about Galton boards, which, you know, technically form a binomial distribution, but can also give us some insight into why the central limit theorem is such a, or really the normal distribution, such a useful approximation of, you know, a lot of different distributions. And just a little bit of more on like the behavior of sampling distributions. All right, so we are right at 2:15. I don't want to hold you guys over. I do appreciate your attention. Do feel free to reach out. Again, if you just Google me, you'll find my email address on my university website, the IU University website. And you know, I hope you've enjoyed the pre-course, and I really hope those of you doing the masters enjoy the year. Thank you.
Thank you so much, Henry. Lots of thanks.